which is ethylene, to produce ethylene oxide by oxidation method, and then this product will be used by team 2 as their raw material to produce acrylic acid by carbonylation of ethylene oxide from beta propionolactone. And then team 3 will use the second raw material, which is propylene, to produce acrolein. And then same goes to team 4. They also use the same raw material, which is propylene, to produce propylene oxide by epoxidation method using hydrogen peroxide. And then this intermediate product will be used by team 5 to produce propylene glycol. And then the main reason why we choose this configuration because it gives the highest weightage analysis compared to other purpose chain. And of course, it will give the most highest profit and sustainability as well. Okay, now moving on to the overall gross profit estimation. The total revenue for product to be sold is about 28,000 million per year, and the total cost for all the reactants used in our chain is around 13,000 million per year. Thus, the overall profit for our integrated plant is around 15,000 million per year. Okay, next is the site selection. We choose Kerteh Industrial Park because it gives the highest weightage analysis in terms of marketing area, raw materials, transportation, availability of labor, and utilities as well as local community consideration.
Moving on, let's look at the overall integrated waste treatment and utility system. Next slide, please. Okay, so this table shows the pool emission requirements from all the teams. It includes cooling water, chill water, refrigerant, until the electricity. So for cooling water, all the teams require it, and the total amount needed is 62 million kg per hour. As for chill water, only team 4 doesn't need it, and the total requirement is 35 million kg per hour. As for the refrigerant, team 1, 2, 3 needs it, and the requirement is 1.5 million kg per hour. As for wastewater, only team 1, 3, and 4 produces wastewater that needs to be treated, and the requirement is 85,000 kg per hour. For demean water, team 4 and 5 requires it, and the total amount is 19,000 kg per hour. As for steam, only team 2 requires steam generation, so the total requirement is 8 tons per hour. As for electricity, all 5 teams require electricity for their auxiliary equipment and so on, and the total requirement is 80,000 kilowatts. Slide, please. That being said, these are the task division for the design team. So team 1 will be handling cooling utility, team 2 will be handling wastewater treatment system, team 3 will be handling demineralized water utility, team 4 heating utility, and team 5 electrical utilities.
All right, thank you so much. So I'll take it from here. For the centralized cooling utility, this is the overall process flow diagram of the cooling utilities that we have designed. So the centralized cooling system consists of chill water system and the cooling water system that utilizing the cooling tower. So as shown in the figure, we have 5 types of stream. We have air, cooling water, chill water, refrigerant supply, as well as a fresh feed water supply. Now, from the cooling tower, the water from the plant will enter at 50 degrees Celsius to be cooled at 30 degrees Celsius. So the supply temperature of cooling water to the condenser for our refrigeration cycle is 30 degrees Celsius, and some is supplied back to the plant that is demanded by the plant, and it will return to cooling tower at 50 degrees Celsius. And in the refrigeration cycle, R7 at 4, liquid vapor mixture is utilized to chill the processed water in the evaporator E102, and before it enters the chiller's compressor. And the cold chill water is at 6 degrees Celsius from evaporator outlet is supplied to the plant for the cooling process for each respective plant.
Thank you. Next, I'm going to talk on the centralized wastewater system in our urban plant. So after we done few technology reviews, we select the membrane bioreactor system MBR as our centralized wastewater treatment technology. It is a technology which combines membrane process and with a biological wastewater treatment process where higher effluent quality of water can achieve. Furthermore, we choose MBR system because it requires less space for installation and it is presented as advanced biological treatment, which is an ideal option for our integrated plant. So as shown in this process flow diagram, the process starts with the raw wastewater from plants enter the storage tank, then the stream is directed to the equalization tank. Then the water will pass through the fine screening first before enter the MBR system. And in the NBR system, it consists of anostic tank, which allow the breakdown of nitrates by bacteria, aeration tank, which allow aerobic biodegradation of organic contaminants, and also the membrane tank. And the water is separated from the activated sludge by membrane ultrafiltration in the membrane tank. And finally, the water will be disinfected by chlorine and stored in the treated water storage for further use to make demineralized water in our plant. So that's all from me. Thank you.
Next, I will be proceeding for the demineralized water utility. So from here, we will take the treated wastewater from Team 2 and process it into the multi-grade filter in order to make sure the removal of all of the existing coarse and either fine particles before proceeding to the next step. And after that, the processing water will be entering the first demineralization process, which is the cation exchange. So at here, the processing water will be entering the cation exchange column in order to undergo the ion exchange with the hydrogen ions. And after that, the processing water will once again undergo another ion exchange in the anion exchange column, which at here, the anion will undergo the ion exchange with the hydroxide ions, and the demineralized water will then be formed. And in order to ensure that the presence of hydrogen and hydroxide ions throughout the demineralization process, the dilute HCl as well as the dilute NaOH will be supplying into both ion exchange columns. And after that, the product of demineralized water will be supplying to 3 different purposes, which is for the startup water, the makeup water, as well as the electricity use water. So that's all for the demineralized water utility.
Hi, I'm Calvin, and I'll be presenting for the centralized steam utility system. So at the boiler, saturated steam 10 bar G will be produced and sent to the process heaters for heat exchange. So after the heat exchange, the steam will leave as saturated liquid, and it will be collected inside a condensate receiver tank. So here we have a makeup dimming water to compensate the loss of the water through the process, such as blow down and vented steam. So all this water will be sent to a deaerator for degas process. So here the dissolved gases in the water will be removed. Then we have a pump to increase the pressure to the operating pressure of the boiler. And we also have a process heat exchanger to preheat the boiler feed water. So for this heat exchanger, we actually use one of the hot stream from Team 2 to preheat the boiler feed water. This is an approach from our pool to minimize the fuel consumption as well as to minimize the cooling requirements by our pool. That's all from me. Thank you.
Okay, moving on to centralized electrical utilities. So it is split into 2 parts, major 2 parts. In the first part, the boiler will produce steam and then it will proceed to the superheater in order to produce superheater steam. After that, the superheater steam will then proceed to the turbines, starting from high pressure, intermediate pressure, and finally to low pressure turbine. The steam is reheated back to superheated temperature before stepping down in the next turbine. The outlet stream is condensed before passing to the deaerator with makeup water for the degassing process. The boiler feed water is then sent to pump to increase the pressure back and to preheated using the heat exchanger before feeding into the boiler, repeating the cycle again. The heat exchanger is also used using the hot stream from Team 2 in order to reduce the cooling requirement. Okay, next slide, please. And these are the future plans and recommendations for the centralized utility of our plant. For the cooling utility, they are going to innovate the uses of refrigerant with zero depleting potential and investment wise. And they will also be estimating the total cost of centralized cooling utilities by using optimization. For the wastewater treatment system, they will research and develop for better improvement of the system. They also collect wastewater from outside and centralize for treatment. Also, they will also fully utilize the treated water produced in order to reduce the cost of water supply from outside. For the demean water utility, the implementation of exchanger will result in the better purity of demineralized water produced. They will also apply conductivity sensors for better performance. As for heating utilities, they will increase the steam generation for sale, and then further heat recovery from the hot process streams, as well as further reduction in the cooling utility equipment. And then for the electrical utilities, they will generate additional electricity for sale for local power grids or TMB and so on. And then they will also integrate electrical requirements of administrative buildings and centralized utilities, etc. And then they will form a local power grid within the integrated site.
Okay, next, let's move on to the overall integrated site layout. So next slide. Firstly, once the site of the plant has been decided, the next important step is to plan the layout of the plant. So therefore, the main factors that being considered when planning the layout of the plant are the first one is the economic consideration as well as the operation and maintenance convenience, and also the future expansion, and lastly, the safety. So the details are tabulated in the table. Next slide. Next, the figure shown is the proposed overall plant layout. All the 5 plants are located in the integrated plant layout. So the site is located with the access of roads to ease the movement of the workers and emergency responders. The space between units should be at least 30 meters or more to prevent any potential hazardous processes. All the buildings in which relatively consist large number of people working are located well away from the plant area to prevent noise and any potential hazardous area. So for the centralized utility buildings, it is placed at the center of the plant to allow for the most efficient flow of pipes to and from the process units. And lastly, the wastewater treatment plant is placed far away from the admin building and employees to reduce the risk of workers being exposed to offensive or distinctive odors. Next slide.
Okay, moving to overall cost and environmental benefit analysis. For centralized utilities costing summary, total bare cost module for urban utilities is around 1,500 million ringgit Malaysia. For raw materials, before all plants were integrated, non-urban cost is around 11,000 million, where raw material at each facility had their own cost value. And when plants employ the urban concept, the cost is reduced to 9 trillion because due to Team 1 product will be used by Team 2. Team 1 product will be used by Team 2 and Team 5 will be receiving product from Team 4. Therefore, cost for raw material can be saved up to 24.75% compared to non-urban concept. Moving to logistic costs, installation of bulk chemicals transportation pipeline cuts expenses on fuel, transportation service contract, and multiple trucks periodic maintenance. Therefore, logistic cost is reduced with 92% savings compared to the use of trucks on the same purpose. For labor cost, labor cost is reduced to 32.21%, where total number of operators per day for urban integrated plant is lower by 372 operators, which non-urban integrated plant requires more operators since each individual plant has their own independent utilities and waste treatment sub-plants. Next is utilities and electricity costs. An integrated system reduces utilities costs covering water and steam usage by 73.21% by applying centralized utility system. For electricity costs, annual electricity cost is reduced by 86.02% by employing the urban concept. Moving for overall profit analysis, undiscounted payback period for non-integrated system is 2.9 years with IRR 46.62%, while payback period for integrated system is 1.1 years with IRR 67.11%. Hence, by implementing urban concept, the integrated plants can start earning profit before half of second operational years. Referring to the discounted cumulative cash flow analysis, integrated system have around 67% of IRR over 20 years operational plan, while non-integrated system only 47% IRR. Hence,
integrated system is more feasible and can sustain longer in business compared to non-integrated system.
Moving on to the environmental benefit analysis. So first is the reduction in wastewater emission. So by recycling and reusing the wastewater to team 3 and 5, we can achieve about 83.53% of reduction of wastewater emissions. Next. So the second is the reduction in energy consumption. So after heat integration is being implemented to the process, we can achieve about 27.32% of reduction. Third is the reduction in carbon footprint. So from here, we can calculate the greenhouse gases emissions reduction that when we reuse the wastewater. Based on the calculation, we achieve about 84% of greenhouse gases emission reduction. Then it's slide before slide. Then the reduction of energy also contributed for the GHG emission reduction with 27.32%. Next slide. And last but not least, for reduction from transportation, in order to calculate the greenhouse gases emission reduction, we assume that the raw materials is being transported through a pipeline for about 0.3 kilometer, and the product will be sent to the port about 1.8 kilometer. So based on these assumptions, we could calculate the reduction from both teams that are using the product from other teams, which is at 7.13% and 29.13%.
Okay, now I will moving on to the conclusions. In line with the Bourbon concept integrated plant, the waste treatment and centralized utilities are implemented to support the needs of each production plant. Hence, the wastewater treatment plant, centralized heating, cooling, drinking water, and electrical utilities are designed specifically for the integrated plant's usage. And furthermore, the integrated plant has a better performance in terms of profitability, which has a lower payback period, and also the business sustainability. And integrated plant also reduce the emission and energy consumption. So that's all from us. Thank you.
Okay, thank you, Pulwan, for the great presentation. So now we will open for Q&A session. Maybe we can start with the first panel. We will start with the industrial panel. Is Mr. Ezral? Ezral, maybe you can start first.
Hi, Assalamualaikum, Pulwan. Very good presentation. It's very interesting to see how you recycle around 80% of your wastewater and turn it into, if I'm not mistaken, diamond water. I'm not sure whether it's practical or not. My question is on the waste gas. How you manage your waste gas? Because I noticed you don't have flare system in your plant. Dengar ke?
Yes, yes.
Okay.
So guys, maybe you can try to answer the question.
Or does your plant did not emit any waste gas?
Yes, true, Mr. Ezra. Our plant actually do not emit any waste gas, just wastewater. So this is why we only have a wastewater treatment system in our pool.
So in case of emergency, that sudden release of gas, so how you manage that? Okay, never mind. Thank you, Pulwan.
Okay, thank you, Mr. Izra, for the question. Moving on to the next one, Mr. Muhammad Firdaus.
Hello everyone, how are you? Do you feel relief after presentation, right? So thank you, good luck in the next for the question, I guess. Okay, so my question first, yeah, because Professor Sharifah has give our reminder lah to so don't expect any perfection from you guys, but we need to challenge you. So the first my question is what improvement your pool made from previous interim and how you close the gap? Because I see there is a 3 recap topics, but you doesn't explain what any comment that you received from previous interim and what you did in this presentation. This is my first question. Then okay, maybe you can answer that first. Do you have or not? Just straight yes or no. If yes, then I can give a good marks. If not, then I have to deduct some marks. I'm taking no, right?
The previous for the previous comment from previous semester, it is that it is in terms of presentation, because the way we presented last semester is based on team by team. So for this semester, what we did is in terms of a presentation, we present in terms of the whole pool. So we try to summarize the information by all the team, and then we present in one go. So this is something that we improved from last semester.
So meaning to say is more on the team's collaboration in how you present it, right?
Yes, correct. It's
okay,
correct.
but it's based on your rubrics, it's more on your improvement in your process lah. But it's okay. The next one on the polling utilities, which is PFD. So maybe you can just quick one. What I didn't understand is there is some missings of 48 tons of the cooling water in your plant basis, which is a chemical plant. You see that if you maybe you can have to check back, maybe I'm wrong. So I see there is recycle. So where is 48 thousands water? You have a cooling water supply, and then you have a receipt of 62, which is returned, but you have additional fresh water feeding is about 62. If I compare this value, is almost the same. There is something lost about 48 and another 1 millions or 1.515 thousand. So maybe you have to check on the mass balance, I think.
How many, sir?
Which one? Do you have to?
May I know? Which part of the mass balance again?
Chemical plant. On the chemical plant boxes,
yeah.
You see there's I didn't see where would be the cooling water return flow rate, which is if I compare, because on the blue line is the refrigerant is a closed loop, so the balance is there. But you see that there is another 3 stream inside, right? But you have one is a refrigerant, but of course it should be a closed loop.
Okay.
Then the water, you have the fresh feed water is about 62 ton, and then you have 48. By right, goes to the cooling tower would be somewhere in hundreds. That is my guess. Yeah, correct me if I'm wrong. Okay.
Because what I think of this operational plan that it operates continuously on our basis of assumption would be 330 days of operation every year. So the fresh feed water supply will be supplied continuously. So the water will just be recycled back and back. That's how I see it. That's why we put the fresh feed water supply there.
Okay, good. But what I didn't understand where there is some losses. You see there is 62 is the same on the return to the cooling tower D100, but where is the 48 one? It should be 100 somewhere if we do simple mass balance calculation. Yeah, just you can check back.
Okay.
And then on the pump, on the P100's pump, the configuration, it should not be like this because there is no any, I don't know, normally it's for centrifugal pump, we don't have 2 nozzle discharge. It should be just a single pipe header, a big header or big pipe, and you have branches which goes to your designated users. So that is my comment. And then so just test you how did you have the redundancy of the pump? You have standby pump or not?
What was it?
Okay, my simple question is, now you have P100. Do you have
Okay.
another standby pump for that, or just single pump?
Actually, the quantity of pump is specified from the right table there. We have
Okay.
11 pump in total. Initially, what I planned was just to check for pump specification, which is the one you mentioned earlier, the centrifugal pump, like the average flow rate capacity that the pump can optimize lah. But then, upon checking again, most of the, based on my sizing and costing calculation, I assume the pump to be a centrifugal pump.
Okay, that's fine. That's good. Just my question is, you have to check on your drawing. So normally we don't draw two discharge line on the single pump. That is
Okay.
my comment. The second is, do you have standby pump? Because normally you see that you have 11 pump. I assume that you have a standby pump, which is we call redundancy. For example, you have P100A, P100B. If you have P100A in maintenance, then you have pump P100B will be on runnings. So that is we call the reliability of your process or your equipment itself.
All right.
Okay. So another one on the centralized wastewater. So what did you do or you plan to do with the sludge or disposed sludge? The drying bag, the kit, the sludge kit. What do you plan to do with that?
That one maybe we can use for landfilling.
What was that?
Landfilling.
You mean you will send to KA?
Yes.
Because it's a considered as a scheduled waste. But you didn't. My question is because you should plan what will we do with this kind of scheduled waste. But in the practical, in the industrial, there is a one we send to KA, but the price is costly. But we do, we can maybe for your information, we can collaborate with the cement industry where they can use as their fuel as a fuel to mix with the coal, pulverized coal, as a because in the sludge there has a calorific value, which is there is a good term of energy for the combustion. And then just for information, for dimming water system, we know any technologies provider doesn't design for 100% of efficiency. As per mentioned by Esral, is it possible or not? Yes, we in BSF we are going to recycle our treated wastewater as you do now, but I didn't understand why you only have one designated storage. It should be two, because some of your treated biological system will be some of failure in high COD. So you need to have a off-spec tank, some sort of off-spec tank. Then one is the good qualities of the tank before you feedings to your drinking water plant. To answer, just to inform you that drinking water normally we design at 80% of efficiency, meaning to say there is a reject water, which is not 100% it will be treated as drinking water. And then to make you safe, because you have put some pressure and on all those that, but according to fluid mechanic principle is it doesn't work on that one bar. Megapascal, kilopascal, right? So maybe you should have a pump somewhere there. Normally we operated this kind of damming water system at 4 bar level. So and then you can fit to, you have your P001 is operated at what pressure header that you want for your system. Okay, last one on the design steam utilities. I don't have the comment, but okay because it's a concept, but actually the concept actually is wrong. But it's okay. You are learning your process, right? I think in general comment, maybe in next sem you have to do more frequent industry visits to understand how steam utilities configuration looks like. Yeah, but it just is my general comment. I think that's all for me. Thank you.
Okay, thank you, Mr. Fidaus. Sorry, thank you. Okay, so since we have limited amount of time, I think I would like to call another panel as representative from UTM. I would like to call Dr. Zaki to give any comments.
Okay, guys. What good that you have presented this, and then I was just about to comment on slide number 12. Just now being commented by IR Firdaus. Dah IR ke belum? Okay.
Not yet. You report.
On the way. Okay.
Yeah.
Okay. Yeah. Okay. So, Mr. Firdaus already mentioned that conceptually the configuration of your steam heating is incorrect. I think your high pressure steam at the next slide also same, not correct. But I want to inquire why you have a pump there. For what reason?
Okay. Can Dr. Zaki, can I answer your question?
Yes, go ahead,
Okay.
please.
So the deaerator is actually operating at a 0.2 bar G. So the outlet, we assume it's at 0.2 bar G. And if we don't have a pump to increase the pressure of the water, so the water can't enter the boiler because the boiler is operating at a 10 bar G.
Okay,
so
wait, Kelvin.
pressure
Hold on.
difference. Okay.
Okay, you already have a very fantastic boiler there, and then the boiler is producing such a magnificent heat energy, 190 degrees Celsius, something like that. And then you have 10 bar, but suddenly, after it passed through the deaerator, the deaerator should be there or not actually. And then how come suddenly the very big pressure suddenly dropped to 0.2 bar? Why?
I see I understand your concern, but this is just based on the assumption because we need to consider the operating condition of the deaerator itself, and from the journal, the deaerator usually they operate at a 0.2 bar G. So
okay,
if
Kelvin,
that's the case, then the outlet should be
Why do you need to have a deaerator there?
Oh, this is actually to remove the dissolved gases from the water.
Do you have a chemical treatment inside your boiler?
No, we don't have that.
So how long do you expect your boiler to last? 10 years, 20 years, 30 years without any chemical treatment?
Okay, because we are using dimming water, so we don't have a chemical treatment for our boiler system, for our steam system.
Okay, so you are very confident that your dimming water quality is okay?
True, yes.
So if that's the case, but then you still need blow down.
Yes, we have a blow down.
That shows that you cannot trust your dimming water as well.
The blow down is actually to control the conductivity of the water.
Okay. It's okay, but overall, I think this need to be improved. You can discuss with your industry supervisor or other supervisor, and then go ahead to the next slide, slide 13. And then we have a high pressure boiler here, which is operated at how many? What kind of high pressure boiler you have here?
Water tube boiler.
Water tube boiler. So this is a closed system?
Yes.
The temperature is up to how much degrees Celsius? I cannot read there.
From the boiler, it's up to 311, and then we have another superheater to superheat until 550.
So the boiler there is actually a high pressure boiler, right?
Yes.
So how do you get that number, 300 degrees Celsius and then 100 bar?
For the boiler, we assume that the boiler will produce saturated steam, saturated vapor steam. So the 311 degrees Celsius is actually the saturated temperature of the 100 bar G steam.
And then amazingly also, you also have a pump there.
Yeah, because same thing, because we refer the same journal. The deaerator itself, from what we saw in the journal, it operates at a 0.2, usually often designed to operate at a 0.2 bar G.
Okay. Okay lah. Thank you very much for your answer. But I wanted to comment more, but I think we don't have much time lah. But I will put the comment inside the evaluation. All right. Thank you. Over to you, Dr. Afiq.
Okay, thank you, Dr. Zaki, for the comments. So those panels who are unable to give comments, you can put the comments into the spreadsheet, and later we will share to the students. So thank you, Pool 1, for your presentation. Now I would like to invite Pool 2 to present your plan design project.
Can you guys see my screen?
Yes, yes.
Okay, so we'll be starting now. So good evening to, good afternoon to all the panels. We are from group 2 and we'll be presenting about our plan design. So this is our table of content. This is our table of content for today's presentations. And first off, for the recap on plan design 1, this is the final purpose reaction configurations with the overall gross profit about 36,000 ringgit per metric ton. And this is the production capacity from all the teams. So I'll pass on to Shahid.
Thanks, Rupong. Now I will present on improvement made from plan design 1. Like, alright. So from previous semester, the comment that have been received is on our site selection analysis, which is we need to add consideration on how to distribute the production to the customer. So from the research that have been made, there are 4 levels of channels that can be used, but the most suitable for our plan is by following channels 2, which is it is start with the manufacturer, and then the manufacturer will send to the distributor, and after that the product will be sent to the retailers before it passes to the customer. Right, next slide. Next, we move to the overall integrated utilities and waste treatment system. As we know that this semester we will be more focusing on centralized waste system and utility system on our main concept. So the centralized waste system has started with a data extraction from each of the design team and then followed by literature review. Okay, next slide. Right. After each of the design team had completed the centralized system, which is wastewater treatment, which will be handled by team 8, waste gas treatment by team 10, heating utilities by team 7, and cooling utilities of cooling water and chill water by team 6 and team 9 respectively. Then all of the design team need to complete their tasks on sizing and costing for their centralized waste system and utility system, and also must verify whether their centralized system is following the urban concept or not by calculating the saving cost by each of the design team. Without further ado, I would like to invite Hafizi as a representative for Team 7 to present on the hot utility system.
Assalamualaikum warahmatullahi wabarakatuh, and hi everyone. Thank you, Shahid. I am busy. Will continue for utility system for Pool 2. Next slide. This is the data obtained from each design team, where Team 7, Team 6, and 7 and 8 need to use flue gas, high pressure steam, medium pressure steam, and low pressure steam to use in their plant. Okay, next slide. So for heating utilities, we use 2 heating medium, which is steam and flue gas. So why we also use flue gas? This is because part of the team need higher temperature to operate the reactor, where HPS temperature cannot achieve. Next slide. This is the literature review for steam and furnace. Next slide. The main advantages of using steam is the water because it is cheap and easy to access, while the furnace requires high energy usage to heat the gas. Next slide. So this is the process flow diagram of steam utilities in Pool 2. So in order to produce 87 and 500 metric tons of steam, the main equipment needed in the plant are water treatment system, aerator, boiler, and condensate tank. The function of the water treatment system is to treat the water before fed into the boiler. So this is to remove any impurities in the water that can damage the pipeline and the equipment. Next is the deaerator. Deaerator was used to remove any dissolved gas after the preheating phase from heater at operating temperature at 80 degrees Celsius. Then the feed water at 80 degrees Celsius enter the boiler to produce high pressure steam, medium pressure steam, low pressure steam, and flue gas by using natural gas as the heating medium. Finally, we distribute the steam needed for each plant, whereas plant 6 need HPS, MPS, and LPS, plant 7 need flue gas, and plant 8 need HPS. The steam will be recycled back into the condensate tank and be fed again into the deaerator. Next slide. So this is the summary of the cost for heating utilities, where the total cost to build out the system is 140 million ringgit. Next slide. In comparison, if you don't make the integrated system, each of the design team need their own heating utilities and will cost about 480 million ringgit. After we do integrated system, we can save 67% of cost for heating in the urban plan concept compared to non-integrated system. Next, I would like to invite Zakwan to present for cooling utilities.
Assalamualaikum, I'm Zakwan from Team 9 and I will present on coal utility system. Next slide. This is the data extracted for the cooling process needed for every plant. Basically, we are using cooling water and chill water as the media for the cooling process. Cooling water will be supplying water at 30 degrees Celsius and chill water will be supplying to every plant. Next slide. This is the PFD for the cooling water system. The process starts with the cooling tower, which supplies 30 degrees Celsius and is pumped to every plant. Then the water returns to the cooling tower at 40 degrees Celsius. Chemical treatments such as scale inhibitors and biocide will be injected into the stream before entering the cooling tower again. Then a blowdown will occur periodically when the concentration of dissolved solid is too high, which can cause scale within the cooling system. Next slide. Next is the chill water system design. The refrigerant cycle will supply chill water at 10 degrees Celsius, which to be pumped to every plant and return to the cycle at 30 degrees Celsius. Will be also a chemical treatment and blow on the cooling tower system to control the water quality. Next slide. Next, a costing summary. So in cooling water section, there will be 6 cells of cooling tower and 3 units of pumps. So for chill water section, there will be 4 cells of cooling tower, a centrifugal compressor, and 4 units of pumps. Altogether, the total bare module cost for overall centralized cooling utilities is estimated to be 58 million ringgit. Next slide. So for non-integrated system, it should have at least 5 cooling tower systems, which are needed for every plant. But for the Verbund integrated system, only needs 2 cooling tower systems. This can also be seen in chill water system design. 1 chiller system is required for every plant, but for the Verbund, it only needs 1 chiller system. So overall, the total cost for integrated system will save 30 million for the non-integrated system. This will save 39% of the estimated total cost. That's all for me. I will pass to the next presenter.
Thank you, Zakwan. I'm Chanvi from Team 10, and I will present about the waste gas treatment. Next slide. This is the data extracted from all the teams. Next slide. The flat system has been chosen due to the high efficiency, lower cost, higher flow rate, and suitable for any concentrations for the gas treatments. Next slide. This will be our process flow diagrams. The waste streams will be first enter the knockout drum at 1 ATM and 40 degrees Celsius. The liquid will be separated out by the knockout drum. 90% of the expected waste gas will be go for the flare gas recovery system, which consists of the compressor and the separator, while the remaining 10% will be go for the flaring by passing through the fresh steel drum first. The fresh steel drum is to prevent the flames from entering the horizontal flare header. The waste gas is then go for flaring in the flare stack. The gas seal in the flare stack actually is to prevent the atmospheric oxygen ingress into the flare stack and thus prevent the formations of an explosive mixture. Next slide. The flaring without recovery will release a huge amount of CO2 into the atmosphere, so we improve our process by adding the flare gas recovery system to reduce the amount of vapor or gas being continuously burned in the flare. This is one of the cleanest solutions to minimize or eliminate the gas flaring. That we have added 2 valves. First is at the inlet of the compressor, while the second is the inlet of the fresh steel drums. The compressor valve will be automatically open under a normal operating conditions, while the fresh steel drums valve will be closed. When the capacity of the compressor is reached its maximum, which is 90%, under the normal conditions, the compressor valve will be closed and the fresh steel drums valve is opened. The 10% of the waste gas which will be flaring is very important to prevent the fresh flow of air. Next. This is the stack gas emission standard obtained from the Environment Quality Clean Air Regulations 1978. The low concentrations of the organic compounds was converted into the CO2 together with water by flaring. Next slide. The total purchase equipment cost needed for the gas treatments will be 1.96 million. Next slide. The total direct cost will be 3.2 million. Next slide. And lastly, the capital investment needed for the gas treatments will be 4.3 million. That's all from for the gas treatments. I will pass to Deepika.
Thank you, Chaiful. I'm Deepika from Team 8 and I'll be presenting on wastewater treatment. So this is the data extracted, and it shows the component that enters for wastewater treatment and the respective mass flow rates. Next slide. So these are the wastewater treatment technologies that we have considered, which are activated sludge, moving bed bioreactor, membrane bioreactor, and biological trickling filter. And we have selected activated sludge as the capital costs are low and their maintenance costs are low as well. Next slide. So this is the process flow diagram for our wastewater treatment. And for this, the design description is that the wastewater will enter the mixer at 85 degrees Celsius and at 180, followed by flowing into the equalization tank. And then it will undergo biological treatment in the aeration tank and the clarifier, where sludge will be formed. And then it will be flowed to the activated sludge tank and pumped to the filter press to become scheduled waste. And lastly, the wastewater is treated and then flowed to the activated carbon to undergo treatment before being discharged from the discharge tank. Next slide. So this is the literature review done on the equipment and their description. Next slide. So this is the effluent discharge standard set by the Malaysian Department of Environment, and our wastewater treatment complies with standard. So that's all from me. And now we will be looking at the total costing summary, where the total bare module cost is 20 million ringgit. So that's all from me, and I'll pass to Chia Yuan to continue with site layout. Thank you.
Thank you, Deepika. And now I'll proceed with the pool plant layout. And next slide. So the plant layout design is shown in the slide, and the plant area buildings are designed as single-story buildings due to the benefit that we listed in the slide. So from the design, we can see that the warehouse is located near the road, while the product storage tank is designed to be located near the process unit that they serve. So this design, we can reduce the transportation cost and improve the plant efficiency. And also the waste handle area is located near the entrance and warehouse, but far from the plant areas to increase the accessibility to the routes and prevent the traffic in the plant area. Besides, we can also see that the chemical plants are designed side to side to increase the plant's efficiency and reduce the piping cost between process unit, while the wastewater treatment system is located between plant group 6 and plant group 10 due to the more significant wastewater production by both chemical plants. And we can actually see from the layout, there are two cooling towers in this urban plant, which are located far away from the heat producing equipment. And lastly, the flare system is located at the top left corner of this pool plant layout. It is located at a downwind location, far from the administration office and the chemical plants, as it can affect human health and increase the probability of fire or explosion to be happen due to malfunction. And next slide. And this slide we shows the pool plant layout. There are 3 assembly points and a few escape routes. So when an emergency such as fire or explosion happens, the employee can utilize the assemble point or escape routes to protect their own safety. And that's all for the pool plant layout, and I'll pass the space to Jali.
Okay, thanks, Jarian. So now I will be presenting overall profitability analysis for our pool. Next. So for percentage cost savings, percentage savings between non-integrated system and verbal integrated system from the aspect of raw material, utility costs, waste treatment system, and labor costs are 33.5%, 99%, 6.7%, and 11.4% respectively. The percentage savings for total expenses is 43%, and the after-tax of return increased from 40.3% for non-integrated system to 19.1% of global integrated system. Next. For cash flow analysis, at plant startup in year 3, no return payback for non-integrated system is 11.1 years, while no return payback for global integrated system is 2.9 years. Meanwhile, the rate of return increases from 6.9% with 19.7 years of payback period for non-integrated system to 37% with 19.3 years of payback period for urban integrated system. Next. So in short, for urban integrated system, the total capital investment is RM 4.71 billion, total expense is RM 8.35 billion, total utility cost is RM 1 billion, total operating labor cost is RM 4.1 million, and after tax return rate is 19.1%. So that's all from me. I will pass it to the next presenter.
Thank you, Jelly. I am Ulia and I will continue to explain about overall sustainability analysis. Next. There will be 108 tons per hour of wastewater sent to the centralized system for the treatment. Recycling and reusing the wastewater as the raw material for a production facility that will need in its operation might reduce the amount. There are 3 plants in the pool that will need water as a raw material. With recycling and reusing the water, it will decrease in wastewater emission by 28%, which also may result in less resource use and less money spent on the purchase of raw materials. Next. As for the reduction in air emission for the greenhouse gas, the Bourbon concept helped to achieve energy saving by 71%. And as some of the raw material for the plant is the product of the other plant, the transportation for the raw material from the supplier could be eliminated, which helped to reduce to 31% from transportation for propylene glycol and ethyl acetate production plant. Next. There are 4 sustainability development goals that we achieve by the Bourbon concept, which starts with SDG 3 by reducing the potential pollution by waste and byproduct. Then by allowing the cost-effective upgrade of industrial infrastructure and modernize of industries can illustrate SDG 9. By recycling and reusing can assist the circular economy in downstream industries in chemical production, which will help the chemical processing sector may go even further, will achieve SDG 12. And lastly, Bourbon concept use less energy, which leads to less waste heat being generated and less greenhouse gas emission. And that's all from me. I will pass the last part to Fong.
So that is all from us from Pluto. Thank you.
Okay, thank you, Pultu, for the presentation. So now we will open for Q&A session. We will start with industrial panel, Ms. Nur Palisa.
You can hear me, right? Thank you, Afiq. Can we go to the slide where you show the emission? No, not the sustainability, but the previous one.
The previous one.
Can you go back? Step by step back. No, it's not this one. It's the emission where you referring to the standard 1978. Okay, all right. This is the stat gas emission standard, right? Okay. Okay. I have 2 questions for this slide. The first slide is it's not a question. It's actually a comment. So the latest emission standard you should follow Clean Air Regulation 2014, not the Quality Air 1978. It's already superseded. Please check the latest standard. And another comment is I cannot see the stat gas at your layout. Can you show me where the stat gas emission is? No, not this one. So the emission is from the flare or emission. Sorry, you were saying that venting, right? Just now. Go back. No. Yeah, this one. Okay. So where does the gas is vented? At which location? Okay. You should identify the location of where you went or your discharge or your emission is, because for this one you need to comply to a certain requirement on the radiation and also on the dispersion limit. So you should identify that in your overall plot, because this one will determine on your overall plot configuration. Okay. So the next one, can we go to the sieve system?
Sorry?
Steam system.
Which slide again? I'm so sorry. Because the line is not that good.
sorry, I cannot remember the example also.
Which part of the slide?
The steam.
Oh, the steam. Okay.
Okay. Do you have you heard of steam drum? Steam drum. Oh, okay. Because you have the steam from your boiler, so you need to there will be a traces of steam where you from the boiler. So do you think you need a steam drum in your steam system? Why you don't have a steam drum here? Okay, maybe what you can do, you can look back at the requirement of the steam drum system.
Can you turn off your mic?
I turned off my mic already.
Okay, okay.
You can hear me? Sorry, maybe the line is bad here.
Clear, clear.
Okay. So normally in a boiler system, you will have a steam drum. This is where you have the blow down, and then this is where you take care of your the steam system. So maybe you can you please look back into your boiler system and check on the requirement of a steam drum here. Okay. I think that's all from me. Thank you.
Okay, thank you for the comments. So I would like to call another industrial panel, Mr. Ezra.
Hi, Pultu. I noticed that you put the standard for your wastewater and emission, despite this has been superseded. I think this one is good. And I noticed that you also put your reference. I think that one also good. And I noticed that in your wastewater treatment plant, you put the pH treatment before entering the aeration basin. Good. And can you go to the plant layout? Does the workshop located in the plant area or outside the plant area?
It's outside but near the plant area.
Okay, okay, good. And can you go to the flare diagram? I want to see the compressor. You have two feet that going into the compressor.
For the first one is about the waste gas, and the others is the compressor oil actually. The compressor oil, that's the liquid ring compressor. Actually, it's the liquid.
Liquid going into the compressor.
Yes.
You cannot have liquid going into the compressor. And I think that's it. All good. Thank you.
Okay, thank you, Mr. Ezra. So now I would like to call another representative from UTM. I would like to call Dr. Lim.
Hello, can you hear my voice? Okay, right. I would like to ask about the steam system. Specifically, do you actually producing any electricity? Hello?
Can you repeat?
Yeah, I'm asking for your steam heating system. Is it actually just a normal steam system or is actually it's a cogeneration system?
I think it's a normal steam system.
Okay. So it's a normal system, right? You didn't really it's not a cogen system, is it?
Called this.
No, cogeneration system.
Yeah, no.
Okay, because what confusing me is actually normally if let's say you are using like sort of like turbine, right? The symbol there. Not sure. Normally, if let's say you are trying to reduce, okay, maybe you will use a pressure reducing valve. So, but in your case, it seems that you are using like a turbine symbol. So I thought that you're going to generate the power. But anyway, this is something that you can consider as well, since you can check your pressure difference. In your case, have you studied about the possibility to generate the power? On the steam system, cogeneration.
Yeah, this didn't.
Sorry?
No, no. We no
Okay.
generate electricity.
Okay. So Taufik, I have no further question.
So thank you, Poll 2, for the presentation. Okay, now I would like to invite next Poll 3. Okay, Poll 3, you can start now.
Okay, so I will start. So greetings to all the panel. And so we'll present on Poll 3. Next slide. Okay, so before we begin, we'll have some recaps. Next slide. Okay, so here is our basically our pool chain, which if you see the arrows there, it shows which one is which each team is producing. So for propylene, you can see from the top side there, the propylene oxide is from team 11, acrylic acid is produced by team 14, butyl acrylate is produced by team 12. And on the ethylene side, we have ethylene oxide produced by team 13, and also the vinyl acetate produced by team 15. And our site selected is Bintulu, Sarawak. Yeah, so I will pass the time to Ku for the next slide.
Alright, so I am Ku Fauzan and we'll proceed to the improvement that have been done based on the interim presentation. Alright, so based on panel comments, so we prepared the rubric for the weightage analysis in the determination of the site selection for our process plant. So from the analysis and comparison of all the potential site, so the site selection process is based on the overall metric with mark given to all the criteria with their respective weightage. So it is very important to have the rubric for every mark given in the analysis. So the detail of the rubric that has been discussed within the pool regarding the advantages and the advantages of each selection criteria. So after weightage analysis is completed, so no changes in the site selection where Bintulu Sarawak is selected as our process plant site location.
So we are team 11. So next. Our team steam distribution system provides steam to each chemical plants within the Verbund concept integrated chemical plants. So for pool 3, we are in charge of the heating utilities, where we will produce high pressure steam, HPS, medium pressure steam, MPS, and low pressure steam, LPS. So for according to the table, for streams with target temperature less than 220 degrees Celsius, LPS will be used. For streams with target temperature in the range of 220 and 310 degrees Celsius, MPS will be used, while HPS will be used for target temperature higher than 310 degrees Celsius. Next. So for our pool heating utilities, each group will calculate their flow rate of the heating medium required via the gram composite curve. This table will show the flow rate needed from all the teams in pool 3 for the heating mediums. In total, 123,000 kilogram per hour of steams are needed. Next. To calculate the amount of fuel needed to generate steams, several assumptions have been made. Firstly, natural gas is used as a as the fuel, consisting of primarily methane, and calorific value is the 47.3 megajoule per kilogram. The boiler thermal efficiency is assumed to be 90%, while the boiler is subjected to 5% blow down water
which means that the makeup water will also be 5% of the steam produced. Using the formula shown, the amount of natural gas required is calculated, which is 6,800 kilogram per hour. Next, for air calculation, we assume that 1 kilogram of fuel will require minimum 17.12 kilogram of air. 15% more of excess air will be supplied to the boiler. Therefore, in this case, 1 kilogram of fuel will require 19.69 kilogram of air. In total, 135,000 kilogram per hour of air or 28,000 kilogram per hour of oxygen will be needed. Next, this is the BFD of our steam boiler system. From here, we can see that HPS in the steam boiler system is produced at 50 bar G and then stepped down to 18 bar G to produce MPS. Then MPS is then stepped down to 9 bar G to produce LPS through the let down valve. The aerator is used to preheat the boiler feed water and remove dissolved gases such as oxygen and carbon dioxide, and the softener is used to reduce the water hardness from condensates. Next, in terms of equipment costing, we have used a total of 15 equipment, which brings to a total bare module cost of 18 million ringgit. Next.
Assalamualaikum and very good morning to all the panels. My name is Muhammad Zakwan bin Muhammad Basini. I am the representative from Team 12. We will present about the chill water utilities. Okay, so in a chill water system, we have three types of utilities. We have cooling water, chill water, and also the refrigerant of ammonia. Okay, next. Okay, so this is the data collection for our pool. Three teams have required for the use of chill water. That is team 11, 12, and team 14. So the total chill water required is 441,000 kilogram per hour. Okay, next. Okay, so this is the process flow diagram. The red line is represent the cooling water cycle. The green line is the refrigerant cycle, and the blue line is for the chill water cycle. Next. Okay, so this is the equipment costing summary. We have cooling tower, pump, condenser, and evaporator and compressor. So the total bare module cost CTVM is about RM 25.7 million. Yeah,
Now, I'm the representative from Team 14. Now we're going to move on to the cooling water utilities for Pool 3. So the cooling water requirement by design team, the utilities are cooling water and refrigerant 1150. And the temperature range is from 30 to 40 degrees Celsius for cooling water, 10 to 30 degrees Celsius for chill water. Refrigerant is first stage is -25 to -15 degrees Celsius. And second stage is -75 to -65 degrees Celsius. Next. So the cooling water requirement by design team is team 11 and team 12 does not utilize any sort of cooling water, while team 13, 14, 15 utilize a grand total of 13,354,124 kilogram per hour of flow rate of water. So the overall centralized cooling water system for pool 3, we using a induced cooling tower with a counterflow current, and there is a quantity of 12 cooling tower will be utilized in this entire design, and the total cooling water flow rate is 13,379,408 kilogram per hour, as well as the air flow rate for the overall cooling tower is 7,800,000, and we'll be utilizing for team 30, plant 13, plant 14, and plant 15. Next. So this is the cooling water system utilized for each of the 12 cooling towers. So each cooling tower will be going through 1,140,000 of kilogram per hour of cooling water, while the air flow rate is 650,000 kilogram per hour. Next. And this is the cooling water, same system, but the unit operation is provided, and the cooling water flow rate is provided for each unit operation of each plant by each team. So the highest flow rate required is team 14, 4 million kilogram per hour. Meanwhile, the lowest is team 15's 42,000 kilogram per hour. Next. So this is the equipment sizing summary for both cooling tower and pump sizing. The weight of the cooling tower, each cooling tower is 64,000, while the pump is the power consumption is 104 horsepower. Next. So the costing summary, there is a grand total of 36 equipments with a bare module cost of 56 million. And last but not least, the profitability analysis for cooling water system. The capital cost is 12,906,000. For centralized and non-centralized, when we compare it, there is a 57% of saving cost from capital cost of cooling water from 95 million to 40 million. For operational cost, there's a saving of 16% from 180,000 to 150,000. Next.
So I'll represent Team 15 to talk about our carbon dioxide treatment specifically. Next slide. Okay, so this is actually the gas waste we collected from each team, but here we want to focus more on the carbon dioxide. So next. So here we actually compiled the flow rate for carbon dioxide specifically. So it comes to about 100,000 kilogram per hour. Next slide. So this is actually our carbon dioxide plant. And the purpose of this is that we do not want to just necessarily remove carbon dioxide. We want to make a profit out of it because carbon dioxide is not necessarily a toxic gas. So we want to make profit by turning it into methanol. So here, there's a few key points I want to highlight. So here you can see that the conversion to CO2 to methanol from the first reactor, and then the recycle. The second reactor is actually to consume out the carbon dioxide the carbon monoxide byproduct, and so to recycle. The last you can see at the end there is the methanol being purified. Next slide. So here's the simulated plant. Next slide. So here is after the heat integrations. So because it's quite intensive on the cooling and heating, so there's two heaters, if you remember from the previous slides. So in here, we can actually manage to save this heating up to about 95% and the cooling about half. So next slide. So there's a few sizing summary. The few parameter we take from the internal simulations, and the all material for construction is carbon steel. Next slide. So this is a summary costing. So in total, this plant costs about 161 million of bare module cost. Next slide. Yes. So in here, I want to specifically look at the two table below. That the total operating cost annually it's about 250,000, but our revenue from the methanol is actually 1 billion. Next slide.
Okay, now moving on to the wastewater treatment. Next slide. Okay, there are 4 streams in total coming from team 11, 13, 14, and 15. And these are the components that are in the table. As you can see, most of the percentage is low, except for monoethanol, amine, and water. Next slide. So since MEA is organic matter, we propose a water treatment method for treatment plant. And then all 4 streams will first go into the mixer and operating at 40 Celsius and 5 ATM for throughout the process, and then it will go to a equalization tank to help suspend any solids present, as well as to ensure a consistent flow to process. And then going into a water treatment, which is aeration tank, to where the microorganism will consume any organic matter with addition of oxygen. And the clarifier will then separate the treated water from the mess and sludge. The digester is used to convert any material into a final stable product before sending it to a filter and going into a solid disposal, which is scheduled waste landfill. And then the treated water and the filtrate will then go into a disinfection process before sending them into a release pool. Next. Okay, these are the equipment sizing for our equipment. Next. Next. And the sizing of all equipment then leads to a bare module cost with a total around 1,279,331 and 27 ringgit Malaysia. And comparing all the costs in the integrated and not integrated, we can save around. It can be seen that the cost for each team after Bourbon is more lower compared to before Bourbons. Next slide.
Assalamualaikum and good day everyone. My name is Hazani and now I will present about food profitability analysis. Okay, so as we know, Bourbon concept has been applied in this plan design and give significant improvement and interesting benefit in terms of profitability. After implementation of the urban concept, several costs has been reduced in our pool centralized system, which are raw material costs, utility costs, and labor costs. For raw material costs, for non-urban, raw material at each facility has their own value cost, which costing around 18.7 billion. And for urban, which connecting our production units with each single plant, clearly acid produced from team 14 is used by team 15, and the overall raw material after urban is costing around 16 billion. Hence, the cost for raw material reduced around 2.7 billion and can be saved up to 14.44% compared to non-urban plant. And for labor costs, for non-centralized system, the annual labor cost is around 8.5 million, while for the urban is 2.4 million. And the cost for non-centralized system is higher because it requires more operators since each plant has their own utilities and waste treatment sub-plant, while less operator needed for centralized system since utility system is integrated. Hence, the total number of operators per day is lower by 212 operators after verbal integration. And the annual labor cost is reduced around 6.1 million with 71.76% saving. Next. For utilities costs, it can be seen that the capital cost and operating cost for centralized system is lower, since non-centralized has their own utilities system for each plant, and each on-plant system require more cost for things like raw material, pump, turbine, compressor, and other utilities. Thus, utility cost is reduced with 66.43% saving. Next.
Next, moving on to the overall profitability analysis. For the total capital investment, we managed to save around 8.7% after integrated to urban plant due to the saving in capital cost in building centralized system and utilities. Also, after integration, we estimate an increment of 4.7% from the revenue sales and 17.5% for the net annual profit after tax. Rate of return also estimate to be higher with the urban side from 53.45% before integration to 68.78% after the integration. Next. For the undiscounted cash flow analysis, from the figure we can see that for the same discounted rate, the urban integrated plan has a higher cost annual profit and a shorter payback period, which is only 1.51 years compared to non-urban, which is 1.96 years. Next. Next, for the discounted cash flow analysis, both cash flow are analyzed over 20 years, excluding 3 years of construction. From the figure, the urban integrated plan has a higher IRR when MPV is 0 compared to non-urban, which are 41.79% before and 49.49% after. So the maximum allowable performance discount rate for the urban integrated is at 49.49%. In conclusion, urban site have a significant improvement in terms of profitability compared to non-urban. That's all for the profitability analysis.
Assalamualaikum and good day. I'm Fatin. I will present on the overall integrated plan layout. So next. So there are a few plan layout consideration, which are first, minimum movement. Second, efficient space utilization, flexibility of working, interdependence of related processes, overall integration, safety, economics, and also work satisfaction. Okay, next, I will pass to Zul.
Assalamualaikum, my name is Zulkifli. So after take consideration which my friends explained here, we come up with this plan layout as we can save a lot of things such as cost and time. For instance, the shorter distance between the plant and the centralized utilities can reduce the pipeline cost. And we also can minimize the product travel distance where the raw materials and product storage are located near the warehouse. Besides that, like we already know, in the urban integrated plant, all the plant's utilities are supplied by the centralized utilities. Therefore, the arrangement of the plant is based on the total hot and cold utilities required, wastewater discharge, and carbon dioxide emission by each plant. Which means, in our case, that plant 14 and plant 18 require more utilities than the rest of the plants. And last but not least, we also consider for every plant there is extra room available for the expansion whenever necessary in the future. Next. Next.
guys. We're going to present the sustainability.
Yeah, go ahead.
Guess I'll yeah, sorry, because one of my members be the line not so good. So I'll continue from this part. On
1
behalf.
minute left.
Yeah, continue. Next slide. Okay, so for our sustainability, so here we have a few key things that we are noticing and some of our objectives to limit poverty and so on. Next slide. So here there's a few things that we have taken into consideration that helps with the sustainability part, like recycling the raw materials, like also to try to counter in terms of the carbon footprints, like as you can see the carbon dioxide plant. Also, that will also help with the climate change, which is addressed here. Next. Yeah, so that's all from here. Thank you.
Okay, thank you, Putri, for the presentation. Now we will open for Q&A session. We will start with the first panel, Mr. Muhammad Firdaus.
Hello, everyone. Okay, just quick one. Maybe you can show me your steam plan, PFD, steam PFD. All right. Steam PFD on steam generations. All right, this one. Okay, maybe you can explain me why P pump 200 from 5 bar to 11 bar, but there is an increment of the temperature about 20 degrees C. And then as well as you can see on the P202 as well. You can see and P201 as well. And then you can explain me why there is a temperature increment. I would say this is much higher. And then this is a pump, not compressor. Maybe you can explain why in your I mean, like, because you are designing this plan, so what is your basis on calculation for this one?
The increment of temperature is we just make the assumptions of the increment because actually after pressure increase through the pump, the temperature will increase as well. So we made the assumption of increment of around 20 degrees Celsius of temperature change. But we focus on the steam condition, which is whether it's saturated, superheated, or even subsaturated. So we made that as our basis during when we made the assumptions.
Okay, but maybe you just my simple suggestion would be maybe you have to check on the Bernoulli principle to see what is Bernoulli principle is talk about. So on the boiler, I see there is one missing stream, which is flue gas. I didn't see, or maybe it's there, but I didn't see it. Because you have a feed water inlet and steam productions, the blow down and the combustions needed, but there is no flue gas line, which is where will be the flue gas will be diverted. That is maybe you have to check on that.
Okay.
And then the last one is the header. Why you choose this kind of graphic as a this header? It looks like for me is a bullet tank. Because when we talk header, normally is just a normal pipe. Is a pipe with and the size more biggest before it goes to directly users. Maybe you can explain why you choose a bullet tank, or is it this is a tank in your opinion, or this is a pipe?
In my opinion, I choose the closest closest graphic that is look like the actual steam header. So I just choose this as our as a graphic to represent our steam header.
Okay, maybe just suggestion for you because you will be a future engineer. So when you draw whatever you have PFD, maybe you can look on the ISA standard, which is how they drawing the PNID, the PFD, because it's not rocket science. There is a lot of standard, but you can see it on ISA standard. Okay, that's all from me. Thank you.
Okay, thank you, Mr. Firdaus. Now I would like to call the next panel, Ms. Nur Palisa.
Okay. Okay. Can you go to the slide, economic slide? Econs, economics, yes. Okay. For your so I assume this one is your you consider labor cost, everything. Do you consider land cost as part of your operating cost? And also how about your other utilities, for example, raw water, electricity, do you consider in your economics? Why I'm asking this because your IRR is how much is that? 40 plus, right? So it's a very big IRR actually. 60. How much is it? Your IRR, yeah, 40 plus. It's about 40 plus. So I just want to confirm that you have considered all of the operating costs when you're doing your profitability analysis.
We did include cooling water tariff cost for annual for monthly annual cost. Then we converted to yearly.
Okay. How about land cost? Do you include them? If you do not include them, can you clarify why?
Oh, actually, I will have to answer that one. So next slide. Next. So actually, this one, in terms of the total capital investment, it's actually also covered the land cost. It's just we didn't list it down here. So basically, from the BAR module, we will actually go through other estimation of calculation and then here we actually get the final capital investment, including land and piping and so on. Yeah.
Okay.
And then
There's a good answer. If your land you include as a capex, meaning you buy the land, so you don't have to include it as part of the operating cost. All right. Thank you very much.
Okay. Now I would like to invite the last panel, Prof. Sharifah.
Okay, thank you very much, everyone. I want to ask a bit on the heating utility side. Maybe we can go back to the heating side. First of all, I think the temperature of your steam is quite high for LPS, MPS, and HPS because normally HPS is around 260 or something, but yours is quite high, up to 400 degrees C. So normally if the temperature is 400 degrees C, if you need to heat up to 400 degrees C, I think even you cannot use hot oil, you have to use flue gas. So I'm just wondering why you guys are, because this temperature are for me quite high lah. So what is your justification?
Actually, initially we also wanted to use a hot oil system together with the steam generation system. But after our meeting with our industrial mentor, he suggested us that actually for the high pressure steam, it can be heated up to 400 degrees Celsius. So which means that we do not need any hot oil system anymore. So this is why.
Okay, so your industrial mentor suggested up to 400, yeah? Okay.
Yes.
Another question is, if you look at your PFD of your steam system again, where do you supply to the process, the steam? Is it the heat exchangers there, like you have HPS heat exchanger, MPS heat exchanger, and so on? are those actually steam being supplied to the processes to all the plants?
Yes.
Okay,
That's
so
the
you just represent it with one heat exchanger lah. Is it?
yeah, yeah.
I think it will be more practical if you just put like the steam, it is being supplied to the plant. And then of course, inside the individual plant, they have their individual heat exchangers at the respective processes. So when you just put a heat exchanger there, it looks quite confusing for me. I think it's better if you put it that it's being sent to the processes at the plant. And then after that, maybe you have some condensate return from the plant. And then after that, that condensate you collect back, and then you recycle back to your boiler and so on. Another thing is, why don't you guys consider cogeneration? Because this is a Verbund plant, it's very big. So if you let down your steam to the next level, actually you lost a lot of energy, and you can actually use this energy to generate electricity. Yeah. Do you guys have any feedback on it?
We did not consider the generation of electricity in our plant.
Yeah, so I would suggest if maybe, because this is a very big plant, right? It's a Verbund plant, so generating both heat as well as electricity will be quite, I believe it will be quite good, since you can get two in one. So instead of just letting down by using valve, putting a turbine there to let down, and at the same time you can have electricity to power your plant would be a better alternative.
Okay.
Okay, that's all from me. Thank you.
Okay, thank you for Sharifah. I think that's all from us for pool 3. Thank you, pool 3. Okay, now moving on to the next one, pool 4. Okay, pool 4, you can start your presentation now.
Before we begin our presentation, can all of us test our mic?
Yes.
Mic testing.
Hello,
Okay,
mic
clear.
testing.
Clear.
Testing.
Hello, hello. Is my voice
Okay.
clear?
Yes.
Oh, my check. Can you hear my voice?
Okay, yes. Alright. Okay, I'll begin. Craig Venter once said, I have the modest goals of replacing the whole petrochemical industry. Our unique Verbund concept is one of the Pool 4's greatest strengths. Assalamualaikum and greetings. My name is Amma. We are from Pool 4, comprises of Team 16 to Team 20. We'll present our final pool outcomes. Next. First, let's recap the key findings for the last semester. 3 possible Verbund value chains had been proposed by Pool 4. According to the weightage analysis, it is convinced to proceed with the value chain 3 as it ranks the highest total mark in terms of the overall gross profit, provides more safety features, environmentally friendly, and thus most efficient sites. Next. After optimization, 59% of ethylene oxide produced by Team 20 is supplied to Team 17 to produce ethylene glycol, while the remaining 41% is sold to the market. Ratio of propylene used for propylene oxide is 0.82, while the remaining 0.18 is used for the acrylic acid production. Acrylic acid is 100% completely supplied to Team 19 to produce butyl acrylate because of the higher market price of butyl acrylate than acrylic acid. CO2 generated by Team 20 is supplied to Team 17. Wastewater generated by Team 18, 19, 20 are collected, treated, and supplied to Team 17. Next.
Thomas Mitch once said, the biggest room in the world is a room for improvement. Greetings, I am Cindy and will continue to present about the process improvement based on the interim presentation. Next. We have changed the site selection from Kuching, Sarawak to Kerteh, Terengganu after considering the comments from the panel. The decision was made through the weightage analysis stated here. We have reviewed the grade given to every site. The mark for plant location, land price, availability of water and electricity are corrected to 5 as Kerteh is a good marketing area and having good supply of water and electricity. Besides, this location is the cheapest when compared to others. After correcting the weightage analysis, Kerteh is selected as the most suitable site. Next.
A sentence fragment quoted by Klaus Martin, a German engineer, goes by as the first industrial revolution used water and steam power to mechanize production, showing the use of steam as a vital key in productions. Hello everyone, my name is Romadoli from Team 20. We'll be representing the centralized heating utilities. Next. This is a process flow diagram of the centralized boiler system used to produce high pressure steam only. It is much cheaper and more efficient to have it centralized instead of on-site. The system consists of two pumps, a compressor, boiler, furnace, condenser, and a deaerator. The steam generator will begin at the boiler, which shoots the water and the recycled condensate to produce superheated steam. A compressor will then compress the steam to the pressure of 55 atm, then supply to the required teams. Condensate recovery, where condensate is reused as it has higher enthalpy, which leads to considerable saving in terms of energy and water resources, as well as improve working conditions and reduce the plant carbon footprints. Why steam as the heat utilities? Because steam is often the prominent and used utilities in chemical plants. Steam has a high heat of condensation, resulting in a high heat production rather than hot oil and flue gas. Heat exchangers that use steams are relatively cheap because condensing steam has a high heat transfer coefficient and it allows for precise temperature control. Natural gas is an excellent choice for fuel because of its high calorific value, easily pipes directly to the boiler, yet is easy to control. It requires a relatively small boiler space. Combustion of natural gas mainly produce carbon dioxide and water, which do not cause serious pollution problems. Next. With assumption the boiler thermal efficiency is 90% and about 50 mole of excess air will be supplied to the boiler. The summary of mass energy balance can be shown on the upper side table on the left. The HPA will be utilized by team 16 and 90 and the required amount can be seen on the bottom side table on the left, where a total of 97,000 kg per hour of HPS is needed. From the table calculations on the right, the amount of fuel required is 6,000 kg per hour. The air required is 0.13 million kg per hour, meaning about 28,000 kg per hour of oxygen is needed. Next. So after the equipment sizing and costing, the equipment cost is summarized and tabulated in the table. Based on the table, the total bare module cost for the centralized heating unit is about RM 158 millions.
The way to build a complex system that works is to build it from very simple system that work. That is according to Kevin Kelly, former author of Wired Magazine. Assalamualaikum and hi, I am Naimatul, representative from Team 17, and I will be presenting Pool 4 centralized cooling utilities. Next. So in our pool cooling utility system, there are three types of coolant that are used, which consists of cooling water, chilled water, and ammonia R717. And the details of each coolant are tabulated as displayed. After we collect the data from each plant in our pool and do all the calculations, we obtain the required amount of the cooling water, chilled water, and ammonia R717. So for our pool, centralized cooling system is a much better option than on-site cooling system, as all plants in our pool requires cooling water, and 4 out of 5 plants require chilled water. Thus, having centralized cooling utilities will significantly save a lot of our costs. Next slide. And this is the data collection of coolants which required for each team in pool 4. Next slide. Now is for the element of novelty for our cooling utility system. From the heat integration of each plant, which is through the grain composite curve, there are a total of 215,000 kg per hour LPS are generated from all plants. So these LPS, which are not being used in our plant, instead of being discarded or selling it, can be used for the feed water of boiler in the heating utilities, which will increase the feed water temperature of the boiler in order to generate steam. So this can give an advantage in terms of the raw material savings for the boiler of the heating utilities. Next. Now is the PSD of the centralized cooling utilities. So during the process, the cooling water from the cooling tower will be flown to the pump 1 before it's split into 2 streams, where the first stream is the cooling water stream that goes straight to the plant that requires it, whereas the other stream will be sent to the R717 cycle to produce chilled water. The cycle consists of condenser, valve, evaporator, and compressor. The chilled water produced then will be sent back to the plant, and the outlet stream for the cooling water will be sent back to the cooling tower, while the chilled water outlet will be flown back to the evaporator. Next slide. Now is the cost required for our pool cooling utility system, which is tabulated as shown. By using CE index is equal to 567 as our base, we'll calculate the total by cost for each equipment required, and the total by module cost is around 255.8 million ringgit Malaysia.
The earth, the air, the land, and the water are not an inheritance from our forefathers, but on loan from our children. So we have to hand over to them at least as it was handed over to us, said by the father of modern India, Mahatma Gandhi. Hi, I am Cindy from Team 19, and I'm going to present about the centralized wastewater treatment system. Next slide. Let's take a look on the chemical composition of the wastewater from team 18, 19, and 20. There's no large solid impurities present in the wastewater, therefore pretreatment is omitted. Besides, the wastewater contains acidic chemical components. Thus, a neutralization process needs to be conducted to adjust the pH. The wastewater contains mainly water, and other chemical components are just a minor part, which then contribute to a relatively lower BOD and COD. As a result, aerobic wastewater treatment is chosen. Among all the aerobic wastewater treatment, activated sludge is used in this wastewater treatment plant as it is low cost, providing a good return on initial investment. Besides, it is also effective at removing BOD and COD. However, the amount and content of wastewater generated might impair effluent quality, and therefore an equalization tank is used to ensure a steady flow rate of the wastewater. The wastewater is treated in centralized wastewater treatment plant because it is suitable for large capacity of wastewater, it requires lesser labors, and it has a lower capital and operating cost. Next slide. So here is the PFD of the wastewater treatment plant. Firstly, the mixer will mix the wastewater coming from team 18, 19, and 20, then pass it to the equalization tank to obtain a steady flow rate. Then the pH of the wastewater will be adjusted in the neutralization tank and flow to the aeration tank. The solid particulates will be removed in the clarifier and then further clarified by passing through the sand filtration. The treated wastewater will be collected in the effluent storage tank and supplied to team 17. At the meantime, the activated sludge will be stored in the activated sludge holding tank. 30% of them will be recycled back to the system, while the rest will be dewatered and disposed of. And here is the mass balance summary for the wastewater treatment plant. Next slide. Moving on to the equipment costing. All equipment used are listed in the table together with its price in both US dollar and ringgit Malaysia. The total capital cost is around 3 million ringgit Malaysia. Thank you.
Any developed one says there's no such thing as away. When we throw anything away, it must go somewhere. Treatment before releasing waste gas is a must. Greetings, I'm Shirley from Team 18 who will present integrated air emission treatment system. Next slide. This table shows the amount and composition of each component in waste gas emitted from our pool. Since CO2 is in large amount, carbon capture and storage system (CCS) is used as a treatment system. CO2 from team 18 will be absorbed out before mixing with another team, as this can result in larger amount of CO2 absorbed. Therefore, carbon capture is done on site at the plant of team 18, while carbon storage is centralized. Next slide. This diagram shows PFD for CCS, which assumptions are listed in the gray box. From the PFD, 90% of CO2 from flue gas in team 18 is absorbed by MEA after passing through the absorber. Then it enters regenerator to regenerate MEA for recycling. Flash column is function to separate CO2 from solvent and water. Then all CO2 steam from team 18 and 17 are pressurized to 15 atm before mixing with team 20 and then compressed to 50 atm before transporting out. Next. Storage of CO2 should be under negative 28 degrees Celsius and 15 bar as in liquid state and transported through pipeline and ship. For CO2 treatments, Penn United Corporation Ltd is identified as the potential buyer due to their carbon cure concrete technology, which is injecting recycled CO2 into fresh concrete. This is also the element of novelty proposed, which we didn't send CO2 for storage in underground like the normal case. Next. Then a total of 18 equipment sizings were calculated. These were used to calculate the capital cost for the treatment system. Next. Then is profitability analysis. The total bare module cost is around 129 million ringgit. Annual sales gain from selling CO2 to another company is around 1 billion ringgit. So this waste treatment system is gaining profit. Next. Using CCS has a lot of advantage in the long run. It can reduce emission at the source, which as much as 20% of total CO2 emission from industrial and energy production facilities. Besides, captured CO2 can enrich concrete, thus increasing the infrastructural durability of the concrete. Next, CCS can also boost the manufacturing operation by making chemicals and plastics such as polyurethanes. The last one is generating additional power during pressurization of CO2 into supercritical fluid in CO2-based steam cycles, thus increasing the efficiency of power generation. Next.
As quoted by Nick Chandy from Forward AI, CEO, the more a business owner knows about their cash flow, the more empowered they become. Now let's analyze whether the project done is profitable or not. Next. A lot of cost reduction could be seen in a way to maximize cost saving. Pool 4 could reduce the raw materials by 64% reduction or 5.5 billion ringgit. The byproducts of one plant can be used as starting materials of another. CO2 produced by Team 18 and 20 is used by Team 17 to produce ethylene glycol. Besides, acrylic acid produced by Team 18 is used by Team 19 to produce butyl acrylate. Next. We realized a 43% saving or 69.7 million ringgit on the logistic transportation cost. This is because in non-Verbund, all raw materials are supplied from the supplier and are transported by truck, while in the Verbund, the pipeline is majorly used as transportation mean. Next. In terms of labour cost, Pool 4 has saved up to 15.5 million ringgit or 39% labour reduction. This is because non-Verbund own plant system requires labour at each production plant for utility and waste treatment system, whereby Verbund system requires only labours at centralized utility and waste treatment system. Next. Besides, we oversee a total cost saving of 6.9 billion ringgit or a 77% reduction in the centralized utility waste system. The reason why the non-Verbund purchasing ranks the highest total cost is that utility purchasing and transportation are expensive. The rank is followed by non-Verbund own plant system, as more cost is needed for raw materials, fuel, pump, turbine, compressor utilities. As the rank goes down, Verbund centralized shows the lowest cost because the less fuel is used and fewer emissions are produced. Next. Overall profitability analysis is depicted in the table. Both total capital investment and total annual manufacturing expenses are lower for after Verbund than before Verbund. After Verbund records a higher net annual profit of 6.9 billion ringgit. Consequently, the after-tax rate of return ROR of after Verbund is almost 4 times higher. Next.
Environment is no one's property to destroy. It's everyone's responsibility to protect, said Mohit Agade, an author and entrepreneur based in India. Assalamualaikum and hi, my name is Muhammad Haikal from Team 16 and I will be presenting Pool 4 environmental/sustainability benefit. Next slide, please. One way to save energy in a plant is to use heat exchanger, as heat exchanger requires less energy to operate. By using heat integration and installing heat exchanger in our pool plant, we obtain a total of 55.66% reduction in energy required. Next slide, please. Carbon footprint reduction is very essential, not only for the sake of our world, but also for our future generation. There are 3 sources of carbon footprint that can be reduced in our plant. First one is wastewater emission, where we obtain 100% reduction. This is because all the wastewater that have been treated will be sent to plant 17 as their raw material. Second one is energy emission, where we obtain 56% reduction, and this is mainly contribute to the installation of heat exchanger. And lastly is transportation emission, where we obtain 65% reduction. Next slide, please. We believe that there are 4 SDGs related to this part. First one is SDG 6, which focus more on reducing wastewater. Second one is SDG 12, and lastly is SDG 3 and SDG 13, which focus more on air emission. Reduced CO2 emission can prevent climate change and also prevent disease related to extreme climate change, such as heat stroke. Next slide, please. Among all the waste and emission our pool produce, we are focusing more on CO2 emission. This is because CO2 emission is kept on increasing every single year, and because of that, the temperature in our world also increase, which cause climate change. Next slide, please. Because of that, our pool solution to this emission is to use CCS technology. Instead of storing captured CO2 underground, our pool plans to sell it to Pan United Corporation Ltd, which is a carbon Q concrete producer in Asia. In addition, with positive reviews coming from agencies and companies around the world about this technology, we are positive that this technology is a perfect solution to reduce CO2 emission. It might cost a lot to operate, but in regards of climate change, the design is as sustainable as of developed countries such as the United States. Although Malaysia is still in the proposal stage and yet to implement CCS technology, our pool positive that this technology is a subject of much interest in the future. We need to make an effort to reduce CO2 from now on instead of waiting for other developed countries to act first, because this is our world and everyone is responsible for it. Next slide, please.
As quoted by Charles Sims, an American designer and architect, design is a plan for arranging elements in such a way as best to accomplish a particular purpose. Hi, I am Ramadali, will be presenting the layout. Next. So this is the overall plan layout for Pool 4, where will be divided into 2 parts, yellow as a non-process area and blue as a process area. Future expansion is allocated for each teams and the plan for business expansion. The assembly area is located near the main entrance and each plant for evacuation during an emergency. Since this is an integrated plant, it will share common facilities. Next. The yellow area is separated 30 meters from the blue area for safety considerations. The plus wind west handling area is located far from the entrance, plant and admission office to avoid traffic in the plant area and disturbance of false smell. The chemical warehouse is located far from the plant and near the back driveway to minimize the loss in the event of a fire and to allow easy access for tankers. Next. The administration building consists of HR, finance, technical, training, and prayer rooms. The medical center is near the border to provide an immediate emergency protocol. Canteen is located near the administration of offices yet far from the blue area to prevent food contamination. The dimension implemented is an average of 10 meters apart to minimize space and time personnel spent. Next. So recommended at least 30 meters apart, but we implemented 50 meters as a greater space is needed for hazardous process. Team 16, 18, and 20 are grouped together as they require raw materials. Team 20 is located near Team 17, so it will supply some of its ethylene oxide to Team 17 to produce ethylene glycol. Same go for Team 18, and will supply some of its acrylic acid to Team 19 to produce butyl acrylate. Regarding utilities, wastewater treatment will treat wastewater produced by Team 18, 19, and 20, and the treated water will be recycled back to Team 17. The wastewater is located near Team 19 as the most producing wastewater. All plants will benefit from cooling water, and 4 out of 5 plants require chilled water. The cooling units are located nearest to the plant that needed the most. Boiler system is located Team 16 and Team 19 since only this team needed it. Team 16, 17, 18, and 20 produce waste gas mainly consisting of CO2. Therefore, CCS is located near this plant. Next.
And now we've moved to the last part of this presentation. The undiscounted payback period of integrated plant after 3 years of startup is 2.95 operational years, which is 11.32 years shorter than before Bourbon. Thus, we have saved a 79% of operational years. This means that after the payback period, which is the 4th year, the plant will begin to create money. The payback period varies based on the discount rate. If I equals to 24%, the NPV is 0 after 20 years of operation following the startup in year 3. Besides, the application of Bourbon concept also help in energy saving and reduce the carbon footprint. From here, we can conclude that the Bourbon system provides more benefits in terms of economic and sustainability. And that brings us to the end. Remember, save 1 unit a day, keep power cut away. You may have a look on the appendix as well. Thank you.
Thank you, Pulfor, for the energetic presentation. So now we will open for Q&A session. I think I will start with the UTM representative first. So I would like to call Dr. Zaki.
Hi, team pool 4. Well done for the amazing and creative presentation. I love it. That's good. Okay, here's my questions. Okay, for slide number 10, which stated boiler utility, the equipment and everything. So this is a general comment. Okay, if you produce if you produce steam using a boiler, and then when you have to do a turnaround or annual shutdown, and then does that mean that because you have 1 unit of boiler only, so the other plants need to shut down? Is this Romaldo's yours? Okay.
Yes.
So how do you respond to that? So do you need to have 2 boiler?
We only use 1 boiler because only 2 teams uses it. But for my research, in some cases, the cost of repair may be high enough, so that replacement, like instant replacement, is actually better in terms of financial decision. So that's why in our plan layout we have an equipment inventory. So when there's shutdowns for the boiler, so we can immediately replace the boiler if they have malfunction.
Okay. So that need to be considering the daily production of that particular plant and so on. Okay, because sometimes a shutdown may not be very good, because especially if this is an unscheduled or a surprise boiler failure. So normally boiler there will be a spare at least. Okay, can you go back to slide number 10 just now? So the same goes for other equipment. Okay, furnace maybe okay 1. Okay, compressor maybe you need more than 1. Deaerator maybe you need more than 1. Condenser maybe you need more than 1, and so on. Okay, so there are a few things that maybe you need to have more than 1 unit, and some major equipment is okay to have 1 unit only. Okay, the same goes for slide number 26. I think for slide number 26 presented by Lee Yi just now, I think you have got some spares. Where's slide 26? Okay, or some of it, pump. Okay, you have one pump, and then what happens if that pump is, broke down? So you need to have spare as well. So this is the same case, okay, for slide number 10 and 26. And then please go to slide number 14. So just now, it stated that this is the novelty. Okay, LPS used for the feed water or boiler in heating utilities generate steam. I don't think this is novel. So this is already being practiced at many places. Okay, so that's one point that I need to highlight. Slide number 15, please. Okay, E101. What kind of heat exchanger is that? Whose responsibility is this?
Condenser.
Condenser. Condenser for condensing water. Okay, so that's a condenser. Or how about 102? What is E102?
Evaporator.
Evaporator. Okay, fair enough. Do you guys have any heat exchanger?
I think supposedly for the condenser, it's supposed to be a heat exchanger.
Okay. So that is E101 should be a heat exchanger lah. Right.
Tapi
Okay.
condenser.
Okay, so from cooling tower, okay, it passed through 101, pump 101, and then go through the, you just corrected, it's a heat exchanger, and then it goes to the plant. Is it something like that? It goes to all plant 16, 17. From E101, it will go through plant 16 to 20. Is it correct like that?
Oh no. From EZ101 is actually cooling water for the R717 cycle, which is the cooling water is not for the plant. It's actually for the cycle R717 ammonia.
Okay, so E101 is what kind of heat exchanger? What type?
I think maybe we will use shell and tube heat exchanger, as it is the most used type of heat exchanger.
Okay, Akal. Okay. My question now is, this is fluid, right? Is it liquid form? Is it?
Yes.
What temperature is it exchanging? Anybody can help? What kind of temperature? 32 to
55.
32 to 55. Okay.
Yeah.
And then water is heat exchanging with what?
Ammonia.
Ammonia. Ammonia is in what form?
Gas to liquid.
Gas to liquid. The ammonia entering from C101 to E101 is in liquid or gas form?
It is in gas form.
In gas form, okay. So are you sure?
Yeah. Vapor to the so it flow out from the condenser to the liquid form, from the gas to the liquid.
So liquid enter the compressor at C101, and then from C101 it goes to E101 in gaseous form. Okay. So Haikal, you're sure?
Yeah. Yes.
So you're sure this is a shell and tube? Or maybe it should be a spiral heat exchanger, or maybe plate and frame heat exchanger. Why shell and tube? Any justification for that? Please do not say it's most popular.
Because in term of cost, maybe it's the most cheapest one compared to.
In terms of cost, Shell and Tube is the most expensive.
Oh, really? Because when we are doing sizing and costing, we found out that if using flat and frame heat exchanger, I think it's much costly compared to shell and tube.
That's not the correct answer, unfortunately. Okay, so I'm not going to tell you the answer now. I'll leave it to you as a mystery. So please consult whoever who has more experience about why you select shell and tube. Okay. Okay. Another one is slide 19. Sorry, suddenly it's quite a lot of questions. Okay, slide 19. This is presented by somebody interesting just now. So the final sludge disposal is supposed to be what schedule waste number? SW204, SW206, SW315 or what? Any clue? If not sure, it's okay. You can just correct that later.
Yeah, I'm not sure about this.
Okay. So because you are going to send this to landfill, landfill is where? Municipal landfill or quality alarm landfill or where?
Quality alarm landfill.
Which is located at? It's okay. So later you check lah.
All right.
Okay. Right. And then so it's interesting that you guys are using CCS. So that's very good. It's very rare that a plant uses CCS like this. So I'm wondering, because you have a lot of plant inside your facility, have you ever considered utilizing the most simplest one, which is to save cost, utility cost, which is rainwater harvesting? Considering you have large rooftop? Just asking, I'm just asking.
That's why we choose CCS, because actually we got a lot of carbon dioxide waste gas and we can.
I have no issue why you choose CCS. I just agree with you just now. I think it's a very good idea. I'm just questioning why you do not consider the more cheaper one, which is using rainwater harvesting. Not to say why you, instead of using CCS, you should use rainwater harvesting, but maybe you can use both. Lee, what do you think?
Can I add?
Yes, go ahead.
Because we pull for concern more about sustainability and environmental benefits, and we just select one of them. We don't select both because we want to prioritize and focus more on the CCS. It could be implemented but we will find out later on. We will find it.
Okay, I respect your answer, but not entirely happy with your answer. Okay, thank you very much. Okay, over to you, Afiq. Okay, well done, team 4. Pool 4. Okay, bye.
Okay, now I would like to invite industrial panel, Mr. Ezra.
Assalamualaikum. It's very interesting. You start your slide with a quote and end with quote. I'm not sure whether we have extra mark for that. Can you go to the wastewater? Okay, this slide on the wastewater treatment. Where do you do the pH treatment and temperature control?
For the pH treatment, we will conduct in the neutralization tank. So for the temperature of the wastewater coming from team 18 and 19 and 20, there's not much temperature varies. So it will enter the mixer and will be cool down there.
Okay. And on the CO2, do you sell your CO2, correct? how you store it? You sell it in a bottle, like a cylinder or bottle, or do you have a storage tank for your CO2?
Evening, sir. I would like to answer for this question. Basically, we are having a storage tank in our plant, but since our potential buyer is at Singapore only, so we would like to supply through pipelines, or we can supply through ship directly.
Where is your customer located?
Singapore.
Singapore. So you have a pipeline through from Crete to Singapore.
No, I mean the pipeline to supply to the storage tank. Then we might maybe supply directly to the potential buyer through ship or tank.
Can you go to the previous slide on the PFD? So here after compressor 3, the CO2 is at 50 atm and 72 degrees C. So I cannot see where it compress and cool to the berapa di 15 bar. Can you go to the next slide? That minus 28 and 15 bar. Yes.
Oh, yeah. Yeah, minus 28 is the storage condition, but we didn't store it, we just transporting it out, so we didn't cool to that temperature.
So from compressor 3, there is a pipeline to CO2 utilization and storage. And that's where you do the compression and cooling.
Yes.
Okay. Why you need a sand filtration in your wastewater?
It is because we need to supply the water to team 17, so we have to ensure the quality of the water before supplying to them. This is why I add a sand filtration beforehand to further clarify the water.
Okay. How much that you recycle from your wastewater?
All the water, treated water, will be supplied to team 17.
Or you do not produce any wastewater?
Yes.
Okay, that's very interesting. And like pool 1, you don't have any waste gas treatment.
We say that the CCS is actually the air emission treatment system.
Okay, what if there is a PSV that there is relief from PSV that contains high amount of hydrocarbon? Is it going to go into the CO2 treatment plant?
Sorry, I don't understand your question. Because our waste gas is mostly CO2, so we treated by CCS.
But you have to consider in the event of the emergency or incidents where your PSV pop, PSV relief. So where do you route the gas from your
I
PSV?
think that will be the flare system, right?
Yes, but do you
Flare
have flare
system
system in your
we
plant?
didn't include here, but maybe later on we can, because just one air emission treatment system is required for each pool. So we have selected carbon capture and storage.
Okay. Okay, thank you, pool 4.
Thank you so much.
Okay, thank you, Mr. Ezral. Okay, last one. I would like to invite Mr. Muhammad Firdaus.
Hi everyone. That's good for the presentation. I think my comment will be just simple one. Can you look on your steam production configuration? I think slide number, just simple, just one. Okay. Could you please explain why you choose compressor to increase the 5 bar, I think, pressure?
Hi, sir.
What is your basis design? Why you choose compressor? I just need to know why.
From our readings, so they say they put compressor because like when the steam released from the vent and then released from the boiler, and then when it's supplied to the teams, some of the pressure will like reduce. So compressor is like to elevate a bit of the pressure so that when it supplied to the other teams, so it can that's the loss of pressure later, like that.
Okay, but we know in practically we don't use compressor lah to increase the pressure, because you imagine that steam boiler is looks like you pressurize something. You should just use a normal valve. Normally we have some sort of valve. You close it to increase the pressure because you're boiling something, because this is closed system, then the vapor pressure will increase. Then at what pressure do you need, and then you can release to the user. For me, there is no compressor in a practical way, but it's good because you have your own justification. But in practically, we don't. There is not a user compressor. It's just normal valve. And then I think that's all, because we are running out of time. Right.
Thank you.
Right.
Okay, thank you, Pool 4, for your presentation. Thank you, Mr. Fidaus, for the comments. Okay, I would like to invite the next pool, Pool 5.
Hello, testing. Can every member please check their mic? Is it okay?
Can you hear me?
Can you hear me?
Testing, testing.
Testing, Afifa, can you hear me?
Yes. Me?
Testing, testing.
Yes, Afifa, I can hear you.
Okay. So this is the full slide, right? I'm presenting the full one, correct? Hello?
Yeah.
Okay. So can we start now?
Yes, you can start now.
Okay, so good evening to all panels. We are Pool 5, which consists of 2021 to 25, and today we'll be presenting about our plant design part 2. So the first thing we'll be talking about is recaps on plant design 1. So essentially, this is our full configuration where we'll be producing acetic acid, ethylene oxide, acrylic acid, propylene oxide, acetylnitrile, and all the gross profit is listed above the chemicals, and the overall gross profit is around 29,000 per metric ton. So these are all the production capacity and the profit that we're having. So the approximate capacity is listed here, where the total profit is estimated to be 5.47 billion ringgit. And the final thing we'll be talking about is the comments and also the improvement part. So the comments that we have from last semester is that we need to improve in terms of pool coordination, such as justification being too team-based rather than pool-based. There's disconnection for chemical suppliers, and the site selection and pool configuration is not synced. So what we did is essentially we just changed the justification to be more pool-based, and we tally up all the information on chemical suppliers, site selection, and also pool configuration drawing. Next.
Start with the centralized system of heating utilities. Next. The type of heating medium that we use is 120 degrees Celsius low pressure steam, 160 degrees Celsius medium pressure steam, 233 degrees Celsius high pressure steam, and for flue gas, the supply temperature is 470 and return temperature is 370. And for the heating mode of the steam are latent heat, and for flue gas is sensible heat. And for the total flow rate of heating medium required, low pressure steam are around 85,000 kg per hour, medium pressure steam 45,000 kg per hour, high pressure steam 52,000 kg per hour, and flue gas is 376 kg per hour.
1000 kg power. Okay, for the system that we employ for our heating utilities are the boiler and furnace system. Next. And these are the condition of steam and flue gas produced within our pool. Next. Okay, so for the PFD of our centralized heating system, the upper part is for the boiler system for steam generation, and the lower part is furnace system for flue gas generation. Okay, so for the high pressure steam is produced in the boiler before sending it to the flash tank to generate medium pressure steam, and then it will send to the steam turbine to generate the electricity, and also another flash tank to generate low pressure steam, which will then be collected by the condensate collection tank before sending them to the deaerator, which join with the makeup water and recycle back to the boiler. And for the flue gas, it is heated in the furnace before sending it to the required plant. And to treat them, we will use the electrostatic precipitator and also the denitrification units. Next. Okay, so for the equipment costing summary, we have 2 flash tank, 1 furnace, 1 boiler, 1 storage tank, 4 condensate collection tank, and 1 heater, which contributes to around 53 million ringgit Malaysia. Next.
Next is the cooling centralized system. Next slide. The cooling system has two parts, which is the cooling water system and chill water system. The cooling water system consists of cooling tower and pump to cool down the water and distribute it across the process plant. The cooling tower used is a mechanical induced draw because it is more efficient due to counter flow plus large flow rate of water needed by the process plant. Next slide. Next is the chill water system, which consists of refrigerant cycle and pump. A refrigerant cycle is used to cool down the chill water into the required temperature. Ammonia R717 is used as refrigerant because of its high efficiency and zero impact on the ozone layer. The innovation in our cycle is the refrigerant is completely phased into gas to increase the heat transfer. Next slide. Firstly, in designing the cooling system, data on the type and amount of cooling utilities required by each team in the pool are collected. These data are extracted from the grand composite curve. Slide. So there are two types of cooling used in pool 5, which is the cooling water and chill water. For the cooling water, the supply temperature is 28 and returned at 38 degrees Celsius. For chill water, the supply temperature is 50 and returned at 30 degrees Celsius. And from the mass and energy balance, the calculation for total flow rate for the coolant is for chill water is 4,000 ton per hour, and for the cool water is 4,000 ton per hour. For the chill water is 1,000 ton per hour, and for the ammonia is 30 ton per hour. Next slide. So this is the flow sheet of the cooling system. The hot water from the process plant and chill water system will enter the cooling tower at 38 degrees Celsius and will be cooled down to 28 degrees Celsius with ambient air. Then the cooling water will go back to the process plant, where some of it will go back to the chill water system. In the refrigerant cycle, the cold water is used to condense the refrigerants. Then the refrigerant is used to reduce the temperature of chill water from 30 to 15 degrees Celsius. Next, the chill water is then distributed across the process plant. Next slide. This is the equipment costing summary. We show the total bare model cost is RM 35 million ringgit. Okay, next slide.
Assalamualaikum and good afternoon, everyone. I am the representative of Team 22 who was assigned to design the oxygen production. Next. The amount of oxygen required in the pool 5 is 3930 tons per day, which 3 out of 5 teams in the pool 5 need oxygen as a part of their process. Since there are many ways to produce oxygen, we had chosen air separation unit system, that system that we use to produce oxygen. Next slide. For the air separation unit, we conduct literature review and we choose cryogenic technology as the technology to produce oxygen, since the purity of the oxygen that obtained from this technology is above 99.5%. This technology also suitable for high volume and high pressure of oxygen. Next slide. Moving on to the PFD of the air separation units. Air compressed twice up, it reached to the 6 atm before sending it to the double column. First column, which is low pressure column, will produce high purity of nitrogen, meanwhile oxygen and argon will be separated in the second column, which is high pressure column. High purity of oxygen is pumped to 35 atm as we standardize our pool to receive oxygen at 35 atm. Next slide. This is the air separation unit costing summary. The total of bare module cost is above 433,000 ringgit, which including 3 storage tanks for oxygen, alcohol, and nitrogen, and also the cooler box, which included in the heat exchanger. That's all for me. I pass to the next presenter.
Good day, everyone. So I'm going to present about waste gas management system. Next slide. So this is the waste gas production of pool 5. As we can see, only 2021 is not contributing any waste gas from their plant. Other teams are contributing to waste gas. Next slide. So this is a summary of the type of waste gas that being produced, the mass flow rate and mass percentage. As we can see, carbon dioxide, oxygen, water vapor, and carbon monoxide are the main contributing waste gas from our pool. Next slide. So we are suggesting gas flaring system. So it's a controlled burning of natural gas that cannot be processed for sale or use. The flare tip at the end of the stack boom is meant to aid an air entrainment into flare, resulting increasing burn efficiency. So the increasing burn efficiency can reduce the amount of carbon emission released by the flare. So the lower flammability level of this gas mixture is 3.25%. So it's the lowest concentration or percentage of a gas or vapor in air capable of producing flash or fire. Next slide. So this is the equipment that we are going to use. It's a knocker down that is used to remove any oil or waste from the relief gas. It will be sent to the wastewater system, and the water vapor travels upward the design velocity, which minimize the entrainment of any liquid droplet at its exit the top of the vessel. Next, the flare stack, it's the gas combustion device used in industry site to burn off waste or unwanted gases. So the flare stack main purpose is to combust wet gas. Next slide. So this is sizing for knockout drum, where we are using vertical flash drum, and it's from stainless steel with the cross-sectional area of 2.53 meter and diameter of 1.79 meter and height of 5.36 meter. The operating condition is going to be 40 degrees Celsius and 1 ATM. Next slide. So for the costing of knockout drum, we are getting bare module cost of RM 145,545 ringgit. Next. For the sizing of the flash stack, we are going to use stainless steel with the design wind velocity of 8.9 meter per second and diameter of 0.668 meters with the operating condition of 148.85 degrees Celsius and 1 ATM. So the costing for flash stack is going to be 2,246,559 ringgit. I'll pass to the next person.
Hello, good morning. Good afternoon. So I'll be the representative for Group 21 in wastewater system. Next. So what we did, we compared the two best methods available in the market, which are the activator sludge and also MBBR, which stands for moving bed biofilter reactor, and found out that activator sludge is better than MBBR. Next. So what we did, we extracted every information we can get from every group from this pool, such as stream temperature, pressure, and composition, and also total flow rate. And we found out that the grand total mass flow rate for pool 5 is around 260,000 kilogram per hour. Next slide. This is the process flow diagram for our centralized wastewater system. So as we now know, based on the composition of each plant, only liquid water is present in the wastewater. Since there's no visible or large contaminant present in the wastewater, physical treatment or pre-treatment can be neglected to reduce cost. Since this every time wastewater, the wastewater plant are designed to be operated at temperature range from room temperature to 40 degree and pressure less than 5 atm. So the first stream is directed to the mixer and also then to a splitter. It will be split into two streams, equalization tank 1 and tank 2. The two equalization tank are proposed in this design to ensure that the continuous storage of wastewater, if either one of the tank undergoes maintenance, the other could do the job. Equalization tank is also the point to access the water characteristic by taking samples from the equalization tank such as BOD, COD, and others. So next we will go through a pH adjustment tank, which is a neutralization tank. to adjust the pH of the wastewater slightly alkaline with pH range at 6 to 9. Then the stream will be separated into two streams sent to aeration 1, tank 1 and tank 2. This is the first biological treatment for the wastewater. This is where biological treatment will happen. Then it will go to activated sludge will be settled in the clarifier and directed to the activated sludge holding tank. Then it will be returned back to the aeration tank. The excess activated sludge will be removed from the system to maintain ideal food to microorganism ratio and sludge to maintain optimum operation. Then the treated wastewater from the clarifier 1 and 2 will be sent to absorption tank with activated carbon absorbent. Activated carbon can aid in filtration process to polish the treatment. Then the treated water will be sent to other groups in this pool. Activated carbon has been chosen as the absorbent in this absorption treatment process. And then activated sludge holding tank will proceed to a filter press and also for sludge disposal, which quality alarm will be responsible, and they are registered under eSwitch, which stand for Electronic Schedule Waste Information System. Next slide. So this is the costing for our centralized wastewater system. The equipment itself costs us around 60 million, and the total waste disposal cost and operation in 1 year is around 4 million. Next slide. So I will pass to my group member.
Assalamualaikum and good evening. My name is Nakidin and I'll be presenting the overall cost benefits. Okay, so for the cost benefits, first we need to analyze the GRC or the gross root capital. So for the total bare module cost before and after the integration would be about 1.44 billion ringgit before and 1.35 billion ringgit after. So the total GRC cost will be about 3.57 billion ringgit before and 2.84 billion ringgit after. Next. So after we consider the GRC, we need to calculate the total capital investment. So for the total capital investment, we include all the factors listed in the table. So the TCI before the integration would be about 12.91 billion ringgit before the integration and 10.27 billion ringgit after the integration. Next. Okay, after we consider the TCI, we need to calculate, we need to find out the after-tax return on investment or the ROI. So the ROI after, before the integration would be about 22.45%, while the ROI after the integration would be about 32.66%. Next. Next, we need to include in the labor cost as it is one of the main impact on the cost. So here we have two tables. First, the table it lists down the division of the centralized system and the utility, the centralized system, which are waste treatment plant and utilities plant. So here we have the list of before the integration and after the integration. So the total number of staff after integration will be about 70%, and the total annual labor cost before integration would be about 2 million ringgit, while after they centralize, it will be about 1.24 million ringgit. Next. So this is the labor cost that we include with the total production plan. So the cost before the centralized plant will be higher than the cost after the centralized plant. Next. So this is the CFRR of the undiscounted non-integrated and integrated plant. So this table is used as a reference. Next. This table is also used as a reference for our cash flow profile. Next. So this is the undiscounted CFRR for when the I is equal to 0%. So we have a lower payback period for the integrated system, integrated plant, which is about 3.44 years after the start of production at year 3, and we have about 5 years of payback period for the non-integrated system after the startup of the plant production. Next. So next we take a look into the discounted CFRR. So we need to find the discounted CFRR. We use the gold seek, and we For the non-integrated plant, they should have a higher payback period and lower net cash income for the same discounted rate. And next, we'll take a look at the cash flow profile for the DCFRR. So for the non-integrated plant, we have for the discounted rate will be 17.23% for the life cycle analysis over 20 years, while the DCFRR or the IRR return after the integration would be about 24.72%. Next. Okay, so this is the data extracted from the DCFRR. So if we take a look at the discounted rate from 0 to 24.72%, the CCF will be, the payback period will increase. And for, if we compare the discounted rate for over a life cycle of 20 years for non-integrated and integrated plant, we could see that the negative value for the non-integrated plant is higher than the integrated plant. And this shows that after integration, the cash flow income at the end of the life cycle, at each life year analysis would be better for integrated. Next. So this is the summary and the savings for each of the aspects that we consider in the total overall cost benefit analysis. So we have a saving of each of the factor and listed in the table, and we have a lower payback period after integration, higher ROI, and higher IRR after integration.
Assalamualaikum and good day to everyone. Next. The centralized utilities or waste treatment system developed in our pool have their own benefits in terms of an environment. For centralized heating utilities, it may reduce the number of boilers needed for every plant to a single boiler only, thus minimizing emission of flue gas toward the environment. And the flue gas was treated in the unit of separation to make sure that the amount of particulate matter or other harmful chemical have been reduced before being released to the environment. Also, there is a production of low, medium, and high pressure steam from hot stream with high temperature instead of using cooling utilities to cool down the stream. Therefore, large pressure stream and cooling utilities required to be produced in our pool. Next. In our pool, each plant is exchanging their heat waste by heat integration to reduce the energy consumption as well as reducing greenhouse gases. It shows that the energy requirement after heat integration become lower, which has decreased the GHG emission by 37%. Next. Besides, as we have a centralized wastewater treatment, the treated water may be recycling or reused back by 3 plants in our pool, which require amount of water for operation of their plant. By doing so, we could reduce the carbon footprint of the plant with the reduction of wastewater emission, and our pool are able to reduce 71% GHG emission per year compared to the non-urban system. Next. By ensuring the cycle is continuous, our centralized cooling utilities are able to minimize the usage of water for water losses. The energy used in cooling utilities also is optimized and efficiently used, which in turn reduce water pollution and usage. Next. In our pool, we are doing flaring to treat the waste gas emission. Despite the fact that flaring brings harm or danger, it is much better than releasing the off-gas to the environment to reduce the pollution of off-gas that can induce more hazards to local communities. Furthermore, the self-production of oxygen in our pool able to achieve cost reduction of outsourcing oxygen supply from local suppliers. Next. And last but not least, as acrylic acid plant obtains their raw material from Tin 23, which produce ethylene oxide as their product, the transportation for raw material from supplier or the selling of product could be eliminated, hence saving the energy as well as reducing the carbon emission from transportation. As a result, 21% of GHG emission from transportation was achieved in our pool. Next.
Okay, now we go to the overall integrated plant layout. Next. This is the proposed plant layout for our pool. So the process plant area, the process units will be separated from the non-process unit to ensure the smooth flow of process materials throughout the operation. And the process plant will be situated far away from the highly populated areas such as offices for safety purpose. The utilities will be located near the production plant to ease the supply of utilities such as chill water, cooling water, and also hot steam. For the storage tanks, for storing the raw materials and product, will be situated at a safe distance from the process units to minimize the loss of raw materials or chemicals produced in case of fire or explosion. For the wastewater treatment, it is located near the process plant area to enable the direct channeling of wastewater from each plant to the treatment plant. For the workshop and laboratory, the workshop will be located not too far away from the plant area for repairs and maintenance of machinery and equipment. The laboratory will be needed for sample analysis such as quality control on feedstock received by the plant intermediate and final product produced from the plant. For the assembly area, in case of an emergency such as fire and explosion, an assembly point will be extremely important to direct the personnel to an area at a safe distance from the hazardous unit. So it will be located near the main entrance. For the expansion area, will be allocated for some major facilities such as process plants, utilities, and also laboratories. This is because it is important to consider the future development of each facility in order to support a potential of a new production line. Next. And that's all from our pool. Thank you.
Okay, thank you Pool 5 for the presentation. Now we will open for Q&A session. We will start with Dr. Lim.
Hi, thanks for the presentation. Can you go to the STEAM system? Yeah, the layout, the STEAM system where you have you showing yeah, can you please enlarge it? Can you explain to me how is the setup of your cogeneration system?
Okay, so for the cogeneration system, we have only one steam turbine, which is connected to the flash tank. So the steam supplied will be the medium pressure steam. So it will produce the low pressure steam and also generate the electricity.
Just wondering why your setup is like rather unusual, because typically they will actually tend to generate, like for example, superheated steam, and in your case you have already generated superheated steam, right? Why not you send to turbine directly to generate the power? Then from there the steam extracted from the turbine that you will use for heating up your process. Just wondering why you choose this setup instead of what I mentioned, which is a typical setup. Do you have any particular reason?
You mean at the steam turbine?
Can you make
Hello,
it louder? I
test.
can't really hear you.
Hello. Is it
Okay.
my okay?
Yeah,
So
I can hear you now.
okay. The Lim asked at the steam turbine, right? Is
Yeah,
it?
yeah.
So the function the value from the medium pressure steam we get from the we will use from the extra value from the medium pressure steam that needed for the pool 5 and the extra we transfer to because it have extra, so we will transfer to the steam turbine to change to low pressure.
Okay. But you have to bear in mind that typically for you to channel the steam to turbine, right, it requires superheated steam. Typically it requires superheated steam instead of saturated steam, because you want to avoid the potential corrosion. If let's say you have any wet steam into the turbine, then it may lead to corrosion. So typically they will use the superheated steam. And typically once you have the superheated steam generated from the boiler, they will just channel it directly into turbine. Then whatever steam remaining that you can actually, after you pass by the superheated steam, then Then the extracted outlet, the steam outlet, then it will be channeled to the end user. So this is a more typical layout. So I'm not sure whether what you propose here, it will be workable or not. So something you need to check. But definitely you can't use saturated steam. Okay, that's
All right,
my
sure.
comment.
Sure. Okay, sure.
Okay, thank you, Dr. Lim. So now I would like to invite industrial panel, since Mr. Ezral is the industrial test. Hello. Can you guys hear me?
Yes.
Okay. Okay, since Mr. Ezra is industrial supervisor for this pool, I will call Miss Norfalisa.
Hello, can you hear me?
Yes.
Okay, I have question on your flare system. Can you go to the slide for your flare system? It's like 20 plus. Right. I notice here you select for your flare knockout drum and your flare is a stainless steel. Why do you choose stainless steel? As the that one, stainless steel as the material of construction. Why do you choose stainless steel, not carbon steel or other type of material?
So it's in industrial nowadays, it's mainly used stainless steel for their best for longer time usage. So I just took from there.
Okay. I think you are aware if we choose stainless steel will be more expensive than carbon steel. So if you decide to use a more expensive material, you need to have a justification for it. It's just not just benchmarking with the industrial standard. It's just benchmarking with what the practice of the industrial. Okay. Another question is on your cooling water. Can you go to your cooling water system?
Supervision?
Cooling water. The cooling water, cooling tower.
Wait, it's lacking from my side. Wait, cooling water.
That's okay. No problem.
This one?
Next. Cooling water supply. Okay. Can you go back to the previous slide? Your utility cooling water supply is at 28 degrees Celsius. So, what are the criteria of you choosing 28 degrees Celsius as the utility supply temperature? And can it be achieved considering the average ambient temperature in Malaysia?
Because I choose 28 because it's the normal ambient temperature in Malaysia. But I assume that the temperature is at standard is 25.
Okay. Why you say 25? Where is your reference? From where you get that reference?
Because the 25 is the standard temperature.
25 is maybe you can get that in Cameron Highland, but average temperature, ambient temperature in Malaysia is above 30 degrees. So normally when you're doing design, especially for the cooling water, you need to check with the site condition. So this site condition on the ambient temperature, wind, for example, or humidity, because designing a cooling tower, humidity is very important. So you can get this data from the meteorological department. So this information is available in the internet. Actually, you can just Google that. Okay. All right. Another another question is for your econs. Do you consider fuel gas in your econ?
Yes, we consider fuel gas under waste gas. No.
Sorry, I cannot hear you actually. Can you repeat, please?
I think yes, we include the flue gas. Is it?
Yes, fuel gas, because you have furnaces, you have boiler, right? So to fire these furnaces and boiler, you need fuel gas. So okay, you can get fuel gas from the off gases from your processes, or if it's not adequate, you need to import the fuel gas. So in your economics basically, as part of the OPEX, you normally consider the fuel gas if you take it from the outside of your boundary. So do you consider the fuel gas in your economics?
I think I consider it in the econs, but not under GRC. It should be under operating.
OPEX.
Yeah, it should be under OPEX.
Okay, if you consider it's good, maybe what you can do, you go revisit your calculation and double confirm. Thank you. That's my comment.
Yes.
Thank you, Ms. Nur Falisa. Okay, last one, I would like to invite Mr. Muhammad Firdaus.
Hello, hi everyone. Ini soalan apa Okay, alright, go through your simple one lah. Okay, on the plot plan, overall plan layout. Okay, I give you a scenario. For example, there is a fire or explosion happen at propylene oxide plant. So there will be two assembly point, first at the security part and the assembly area. Okay, so how you consider the execution plan for operational plan or whatever operational personnel from the plant site to which assembly area? First, this is my first question.
Okay. In case of fire in a propylene oxide plant, right?
Okay.
So the personnel will so all the workers and employees will use the main road to the assembly area near the main office.
Main office, which is will be on
the bottom left.
Okay. So meaning so what is purpose of assembly area at the security one?
So in case there is fire at the top side, so the employees will be gathering at the assembly area at the bottom one at near the main office, and the firefighters can use the assembly area at the top to go to the place where the explosion happened.
Okay. For assembly area on the main assembly area, what would be the radius? The safe location. I mean, like the distance between the main assembly area and the plant area. What is the numbers? Just give me the numbers. Do you consider that distance? For example, there is explosion, so there will be a radius for explosion, or maybe a toxic chemical release. Then what would be the distance in your opinion? I mean, like because you're designing your plan, right?
Yes. Yes, sir. So in my opinion, the distance should be safe around 100 and above.
100 meters. So meaning if there is a fire or explosion happen in the plant,
From
so
the assembly
people,
line, sir.
so means that all the operational personnel who are working in the process area needs to walk over 100 meters in order to reach the assembly area, right?
Yes, sir. Mainly they will use the main road. So the main road will connect from the plant process area to the assembly area.
So they can go anywhere unless they have the finding the main road. Yep.
Yes. Yes, sir.
Okay. All right. I think that's all from me.
Thank you, Mr. Firdaus. So
Thank you, sir.
I think that's all from us. Thank you, Pool 5, for your presentation. Okay, now we will move to the next presenter, Pool 6. Okay, Pool 6, you can start your presentation now.
Can everyone see my screen?
Yes.
Okay. All right. Assalamualaikum warahmatullahi wabarakatuh, and very good evening to all the panels and all my friends. So we are from Pool 6 going to present about our plant design progress. So I'm going to start my presentation by giving some overview from the plant design one. All right. So this is our, So this is our overall size value chain. So with the overall gross profit of 52,000 per metric ton. So why we are choosing this value chain is because of the high overall profit, the high market demand, which this also produce the less side products. And then the side product acetic acid will be supplied back to the acetylation reaction, and it will produce high product yield. Besides that, we also have acetaldehyde as side product, which can be sold at 4,000 ringgit per ton. And also the side product of water also can be reused in the boilers. So this is at the estimated production capacity by all the design teams from design team 26 until team 30.
So in plant design 2, we have made some amendments based on the comments after the interim. Please go back to
Sorry.
The previous slide. Yeah, this one. Okay. So in plant design 2, we have made some amendments based on comments after interim presentation. So more information is provided on site location study, especially on raw material, logistic, and utilities for construction of plants. Besides, the plant is proposed to operate for 365 days annually instead of 330 days for textbook reference. Next. So for centralized and waste treatment system, Team 26 design waste gas system, Team 27, 28 handle cooling utilities, while Team 29 is responsible for heating utilities, while Team 30 design wastewater treatment system. Next.
Okay, so next I will be continue to on the centralized utilities for cooling utilities. Next slide. So generally, there are two types of cooling that will be used by each plant in Pool 6, which are cooling water and chill water. So as we can see, this is the data collection from each plant, and we found that the total flow rate for cooling water is around 10 million kilogram per hour, while as for chill water is 8 million kilogram per hour. Okay, next. Okay, so this is the selection of type of refrigerant that will be used in the refrigeration cycle, which is R717, specifically to the ammonia that are selected to be used as the refrigerant, where as shown in the comparison in table, R717 possess the good global warming potential, have a low flammability, less toxicity, and also quite affordable compared to other refrigerants such as R290 and R134A. Next. So this is the summary of coolant use, and as shown in the table, there is a standardized range temperature for each type of coolant. Okay, below is the mass balance for R717 that will be used. That will be approximately 1.1 million kilogram per hour and 29 for R717 required in the refrigerant cycle, and 29.7 million kilogram per hour for the cooling water, also 8 million kilogram per hour for a total of the chill water. So we decided to use only one cooling tower based on the XPS cooling technology, as the maximum flow rate is 200 million kilogram per hour. Okay, next. So this is the example for the water makeup calculation, and there are some assumptions applied during the calculation as shown. Okay, next. So this is the overall process flow diagram for cooling utilities. So where there is a cool water out from the tower that will be distributed into two streams, which is first to the directly to the plant, and next is the flow. The stream will be to the condenser so that it can proceed with the refrigeration cycle to produce the chill water to the plants. So the chill water out from evaporator will be pumped out through the plants, and the hot chill goes back to evaporator to undergo the same process. Okay, next. So this is the costing summary for cooling utilities, where as shown, where the total costing for both cooling and chill water system are around 668 million Malaysia ringgit.
Thank you. Now I'd like to continue with the heating utilities. For our heating utilities, steam is chosen as our hot utility. Next slide. Okay, this table shows the standardized heating medium. Next slide. And this table shows the summary of design team flow rate needed. From here, we can see that all design teams needed LPS, and the total flow rate that is required is approximately 271,000 kilogram per hour. Design teams 28 and 29 needed MPS, and total flow rate that is required is approximately 185,000 kilogram per hour. Only design team 29 needed HPS, so the total flow rate is required is approximately 124,000 kilogram per hour. So in total, the steam flow rate that is needed in overall is approximately 581,000 kilogram per hour. For flue gas, only design team 27 is needed. So the total flow rate gas that is needed in overall is approximately 123,000 kilogram per hour. Next slide. Okay, from here we can see the stream where we use values. Here we can conclude that we managed to calculate the flow rates of NPS, HPS, LPS as well as our flue gas. Next slide. Next slide. Okay, this figure shows the PFD of our heating utilities. And based on the PFD next slide. Okay, based on the PFD that has shown earlier, several justifications can be made. Initially, we came up with a PFD with separate streams of air and fuel that fed to the boiler. Since we need to come up with an innovation, we decided to pre-mix and preheat the air and fuel before we send to the boiler. This is because it can increases the boiler efficiency. And also for the air-fuel ratio, we decided as 10:1. This is because to increase the fuel gas quality. Finally, the flue gas is produced more than required. This is because if flue gas is produced to exact amount, the amount of fuel and air will be decreased. So there will be no enough heat to produce steam since we will be using a fire tube boiler. Next slide. Okay, this table shows the heating utilities costing summary. So the total bare module cost is approximately 149 million ringgit Malaysia. Thank you.
So I'll be continuing for centralized gases waste. Next slide. So these are the amount of waste gas released from each steam, which is tabulated in this table. Two treatment options have been proposed. Next slide. Option 1 is flare gas recovery system with flaring. So now let's see the difference between the ordinary flaring system and flare gas recovery system. The ordinary flaring system was mainly used for getting rid of waste gases from chemical plants where it has major drawbacks, which it creates trade-off emissions such as nitrogen oxide, sulfur dioxide, carbon dioxide, which cause greenhouse effect. Thus, a flare gas recovery system is proposed due to its new technology by recovering flare gas before they are combusted by the flares. So if we recover the gas and change it to hydrocarbon liquid, we will be able to send the hydrocarbon liquid to Team 29 to be used as fuel. Next slide. So this is our option 2, which is carbon capture utilization system, which is called as CCU. So the main purpose of this system is to reduce the carbon dioxide emission by capturing and selling it. If we sell the captured CO2, it has high demand in food and beverages and medical industries. Even though it has several benefits, this method is not chosen as it is less profitable compared to flare gas recovery system. Having flare gas recovery system, we can provide recovered gases and liquid hydrocarbon to pools, hot utility steam to supply heat to process heaters. Next slide. So moving on to the chosen options PFD, the waste gas enters the knockout drum where the water is eliminated from it. So we have assumed that 90% of gases were recovered while the remaining gases were flat. So after the 90% of waste gases enter the liquid ring compressor, N-octane and propene is compressed to change its state to liquid and finally separated by three-phase separators. So next slide. So this is the mass balance calculation for our final equipment, which is three-phase separator. From this, we can see that the recovered hydrocarbon liquid is 6.27 exponent 3 kilogram per hour, while the gases recovered is 8.50 exponent 5 kilogram per hour. Next slide. So this is the summary of energy balance for three-phase separator. Next slide. So finally, this is our total bare module cost for our gas recovery system after calculating the costing for each equipment, which is RM 142 million. Next slide. Thank you.
Okay, good day, everyone. I will be presenting for the centralized wastewater. Next slide. Okay, several chemical effluents are released by the chemical plants such as wastewater, acetaldehyde, acetylene, diisopropyl ether, methanol, propylene oxide, and finally acetonitrile with a total flow rate of 177,432 of kilogram per hour, and in meter cube per hour is 178.36. Next slide. This is the process flow diagram for the wastewater treatment system that we come out with, which is the conventional method. Industries nowadays are moving to the conventional method because it is cheap compared to other alternatives such as waste incinerator because it is much more expensive. So the chemical effluents released by the chemical plants will be mixed together in a mixer and will be channeled to the screens and grids to remove the heavy particles, and then further sent to the neutralization tank to adjust the pH, and it is channeled to the clarifier where the heavy particles will be sedimented and will be channeled through the sludge digester for the anaerobic digestion. The treated water will be pumped back to the aeration tank and it will be further sent to the secondary clarifier for treatment. And then reverse osmosis membrane is used to purify the water. And then as a final stage of to treat the water will be the UV disinfection tank. Next slide. So this is the equipment costing summary for the all units. The total equipment cost will be around 15 million. There are few assumptions are made in the mass balance calculation, which are inlet equal to outlet for the screens and grids. 70% of dried sludge will be produced from the sludge dewatering, and the MLSS value is 3000 milligram per liter, and the RAS value is 7500 milligram per liter. Next slide. So the reverse osmosis membrane has a pore size of less than 0.5 nanometers, and it has the capability to treat around 522,987 gallons per day of water. The purified water will be sent back to the chemical plants for reuse and to minimize the waste to the chemical plants which use the water as a resource, as a raw material. For the disinfection tank, the disinfectants used are chlorine, chloramine, and chlorine dioxide, and the retention time will be 30 minutes. And for the sludge digester tank, the BOD removes around 85 to 92%. That's all from me. Thank you.
Assalamu alaikum and good afternoon. I'll be presenting the pool profitability analysis. Next slide. So this is the manufacturing cost summary of before Verbund and after Verbund integration, which includes the manufacturing expenses like direct production cost, utilities, wastewater treatment, and indirect production cost, and so on. Next. So for the percentage cost savings, we did consider the waste treatment system, utilities, labor cost, raw material, So we had the savings of around 13%, 75%, 11%, and 29% respectively. And for the total expenses, we had the savings of around 80%. And for the after-tax return, we had the return before centralization is 25%, and after centralization, it was around 79%, which shows the significant improvement. Next. So for the undiscounted cumulative cash flow comparison, payback period achieved before integration was around 2.1 years, where the payback period after integration was around 1.1 years. Next. So this is the discounted cumulative cash flow for the non-integrated system, and the IRR calculated was found to be around 67%. Next. And for the integrated system, the IRR was around 88%. So that's all for profitability. I'll pass to the next person.
Right, thank you, Animesh, and good evening to all panels. I am Umar Ilyani. Let's continue with pool plan layout. Next slide. So this is the overall layout that we have come out with. I will directly explain the justification for each purpose of our decision in designing our layout this way. Firstly, the entrance. A building that located near to the entrance is because of the movement requirement based on the function of the utilities building. Next, the general facilities. We have the office, administration, canteen, workshop, and warehouse that are located near to the main entrance, which is effective for both internal and external effect. Next, medical and safety center, which is a very crucial and important facility for a chemical plant. We also locate all the centralized utilities near to all the individual chemical plant. Next, I will explain on why we decided to split the chemical plant into two groups, a group of team 26, 30, and 27, and then another group of team 29 and 28. Next slide, please. As you can see at the value chain reaction diagram that I have included in this slide, there is actually three teams working with the raw material profiling, which is team 27, 28, and 29. But since we applying some kind of urban concept to utilize the material, so team 27 will be passing their byproduct acetic acid to team 30. They also receive acetic acid from team 26. So this decision is a plus point for the transportation purpose. All right, next for the storage and packaging, we locate it near to back and side entrance for the ease of the truck loading movement, and also far from the heating and cooling utilities to keep the chemical material in the required condition. For expansion, I would say that all the chemical plant has its own dedicated expansion area, but for this case, we dedicate the expansion area for urban concept purpose, such as for the technology growth in the future. We also have the other utilities such as fire station and the building waste handling area, and also R&D lab. Moving on to the emergency plan layout, we just add some emergency signage of fire extinguisher, fire alarm, emergency phone, and first aid kit. Can we move to the next slide, please? Thank you. So this is our plan with all the signage that I have mentioned, together with the evacuation route shown in the red arrow that is useful for staff and visitor during those unwanted emergency events. We also assign some area especially for assembly point during the emergency cases, which is located near to the chemical plant and also the entrance. That's all from plan layout. Passing to the next presenter.
I will continue to explain about overall environmental analysis for our pool. Next slide. By applying the Verbund concept in our plant design, we analyze two comparisons for the sustainable analysis, which is a reduction of wastewater emission before and after Verbund, and also energy consumption before and after the exchange of heat. These two reductions will also help in reducing the carbon footprint of our plant. Next slide. For the first analysis, by applying a Verbund concept, we got to reduce the wastewater emission by recycling and reusing water to be the raw material for the production plant that we require water in the operation. Meanwhile, for the second analysis, we reduce the energy consumption of the plant in the Verbund system by the exchange of heat. And in this slide, we can see there is a significant difference amount in both analysis before and after applying the Verbund concept. Next slide. Next, we also analyze the carbon footprint reduction by calculating the greenhouse gases emissions. For the calculation part, there are several assumptions that we made. As shown in the slide, after we did the calculation, it can be concluded that by introducing the Verbund system into the project design, the greenhouse gases emissions could be greatly reduced with a percentage of 92.96% in wastewater emissions, and the production plant could achieve a total energy saving of 75.64%. Next slide. There are 4 sustainable development goals that are related to our plant. And our chemical plants that use urban ideas seem to follow this SDG since we utilize and maximize the usage of the waste to reuse and recycle as our raw material. And also we minimize the generation of waste that impact the surrounding and environment. That's all from our pool. Thank you.
Okay, thank you, Pool 6, for your presentation. I would like to call Prof. Shah. Maybe you can start first.
Okay, thank you very much. I think it's quite a good presentation. I'm just wondering for your wastewater treatment, are you treating it up to clean water level actually? Or just enough for discharge according to the DOE standard?
Up to the DOE standard, but the reason why we use the reverse osmosis membrane because we found out that the acrolein toxicity level is quite high, so that's why we wanted to use RO membrane so that it is less toxic. It reduces the toxicity level.
Which plant is producing those toxic wastewater?
May I know which plant produced the acrolein for pool 6? I think it is
27, team 27, I guess.
I think one of your strategies that you can also segregate some of your wastewater. For example, let's say one of the plant is producing some toxic wastewater. So you can separate it a bit. Maybe you have a separate treatment for that. Instead of if you mix all of them, then you will have to treat all of them using the same treatment unit. So this is also one of the strategy if we want to reduce the size of the complex treatment unit. We can segregate some parts of the wastewater as well in order to not to have such big system. Yeah. Okay, that's one. Because you also have UV disinfection. Why do you need UV disinfection?
It's like final stage to reduce the toxicity level. The same reason because of the toxic level.
I thought UV is more for bacterial, like to remove the pathogen and so on. Are you sure it's to reduce toxicity? I'm not really sure that UV can reduce toxicity. I know normally we use it maybe to replace chlorination or something. Maybe you guys can check on that.
Okay, sure.
Another thing is on the cooling utility side. I can see that you only have one cooling tower, which is quite unusual for a very big plant. Normally, if you go to the industries, there are a lot of cooling towers that you can see, very many cooling towers, not only one. So I don't really agree that you have one big cooling tower. If you see the number of equipment, you guys have the number of equipments, right? I think this one you should relook because as a previous panel has also commented, you should always think that, okay, what if suddenly that cooling tower, the only cooling tower fail? So all the plants that's using that cooling utilities have to shut down. So normally we'll have several units of this system so that if some of them shut down or need maintenance and so on, at least we can still, we can have a standby, or maybe we can also let's say one or two is down, so only set one plant maybe is affected, the others can still run as usual. Yeah, so that is something that you guys should consider as well. Okay, that's all from me. Thank you.
Okay, thank you, Prof. Shah, for the comments. So I would like to invite next panel, Mr. Ezra.
Assalamualaikum, pool 6. Where is your plant located? Location, where is your
Bing Pahang.
Okay, Bing. How you get your hydrogen peroxide? How to get your hydrogen peroxide through truck or through pipeline?
I'll be answering this question. Actually, for the hydrogen peroxide, which is used from by Team 29, we actually producing our hydrogen peroxide by ourselves
Ah, okay.
using hydrogen and oxygen.
Hydrogen and oxygen.
Yep.
Where you get the hydrogen?
Buy it
Buy it from?
from Europe, I guess.
Europe.
Yep.
Is there any plant in Gebeng that producing hydrogen? Is there a plant in Gebeng that producing hydrogen?
In Gebeng in general or our own?
Do you know where you get your supplier? Who is your supplier? You have plant that producing hydrogen, okay. And can you go back to your wastewater layout diagram? I think your wastewater is overkill. I don't think it's economically viable to have this kind of wastewater treatment plant. Why you need a clarifier before the aeration tank?
So that the heavy particles will be settled down and will be sent to the sludge digester.
And then you recycle it back to the aeration tank. The sludge that you remove in the first clarifier will be recycled back into the aeration tank. Kan? At stream 15. 13. You remove in clarifier, it goes to the sludge digester and recycle it back to the aeration tank.
Yes, sir. Recycling that.
Very interesting. So where the sludge from the second clarifier goes?
Later it will be sent to the waste treatment to the as a what sludge. It will be sent to the further treatment to maybe to other place. It's just not shown in the diagram.
Okay, that's all from me. Thank you.
Thank you, Mr. Ezral. So I would like to invite another panel. Ms. Nurfalisa.
Hello. Okay. Can you go to the carbon capture slides? Okay. So for the carbon capture, you are capturing the flue gas from your fuel burning equipment, right? So the absorber is typically operated at 1 ATM. It's about 15 degrees C. So how do you transport or how you flow the flue gas from the let's say furnaces to this absorber, because the pressure is about the same. So what like equipment you introduce for this purpose?
Sorry, Miss. Maybe there is misunderstanding about this. For our waste gas emission, we suggest two options, but we only use the option one. We did not use this carbon capture utilization system.
Oh, okay. Sorry. So if you do not use this, why do you recommend that way? Why you choose the other method instead of this carbon capture?
All right. For the reason why you are choosing the option one, like been mentioned before from the presentation, we are not choosing this option because the profitability we are considering about the profitability, which is this CCU technology is quite expensive from the flare system design. So that's why we choose the option 1.
Okay, right. So your venting it actually, venting the flue gas instead of capturing it, right?
Correct.
Okay. And then I have another question. Can you go for your the layout, please? Your plant layout. Okay. I see you have the future expansion at the warehouse area and the waste handling area. This is provision for what?
So for the future expansion, we actually believe that all the chemical plant has its own dedicated future expansion for the chemical plant. So the future expansion that we dedicate for this urban pool layout is for the technology growth for any other technology in the future.
Technology for the utilities or the plant itself? Because I see here you have the expansion for utilities, but for the process itself, you don't have any provision for the future expansion.
For the process, in each individual plant, it's actually have the future expansion actually.
Okay, maybe you...
Yeah, there is actually a dedicated future expansion area for the chemical plant, the process.
Okay, all right, understand. And another question is for your this slides also for your assembly area, because I notice here the assembly area for the cooling and heating utilities, you have to pass through the process area to the assembly area. Why don't you consider the left side as the assembly area for that for the cooling and utilities, cooling and heating utilities?
Oh, okay. So actually, at the first stage, we only try to put the assembly area nearer to the process plant. So I think we can actually add it next.
Okay. I have another question for your GHG. I forgot the slide number. Is it? Can you go to the GHG reduction? I think you have one slide for that. Okay. Here you explain how you reduce your carbon footprint, right? From the wastewater emission and energy consumption. Can you elaborate how you reduce the carbon footprint at the wastewater as a wastewater emission? Like what type of sources? Where are the sources and what GHG you consider? Methane, carbon dioxide, nitrous oxide. What do you reduce here?
Oh, okay. So from wastewater emission, we actually reduce the greenhouse gases by reuse and recycle the wastewater to the to the plant that require water in the operation. I think for the greenhouse gases that we reduce is actually the carbon dioxide.
Okay, are you saying you reduce about 200,000 of carbon dioxide by having a integrated system? Is that correct?
Yes.
So the wastewater. So if that's the case, your wastewater contain a lot of CO2. Which wastewater is contributing to that?
Because from our plant, actually there are 4 plants that will emit the waste water.
Okay.
So because of that, I think that is the reason why our CO2 is very high.
Okay. How many percentage of CO2 in your wastewater actually? Because this reduction is very big.
Before bourbon?
Yeah, before and after bourbon. The which normally when you have wastewater from various plants, you will do a characterization like characterization. Characterization is where you identify what's inside your wastewater, and then from here you will decide on the treatment facility, what you need treatment for your wastewater. So from here, when you say you have a reduction of 93% of CO2 from wastewater, so you need to understand. I need to understand from which sources this CO2 reduction is from, because this is a very it's not a very common number to have this 93% reduction from the wastewater alone?
I think because we did the assumption by for the calculation, we did the assumption by calculating only the overall water emission. That's why we got a very high value for the greenhouse gases emission. We did not consider the CO2 content in the each plant. We just total it up and calculate based on our pool.
Okay, all right, I understand. So what my suggestion is for this carbon footprint reduction, maybe you need to go through maybe API compendium. There has a guideline on the GHG gases and how to estimate it. And then maybe you need to revisit again your number for the wastewater emission.
Okay, understood.
Okay. Thank you, Ms. Nur Falisa, and thank you, Pool 6, for your presentation. Okay, I would like to invite the last pool, Pool 7. Okay, Pool 7, you can start your presentation now.
Okay, a very good evening to fellow panel and my fellow classmates. So we are from Pool 7 and we will be presenting urban petrochem plant design. So next slide, please. Okay, so this is a recap on the urban system from our last semester. So this shows the value chain of our urban plant. So the reason why we chose this is because it has a high profit, high market demand. Side product from one reaction is utilized as a reactant in another reaction. Okay, next. Can you go to the previous slide, please? Okay, so this is the production capacity, the approximate capacity in metric ton per year for each of the design team. So we'll be producing ethylene dichloride, vinyl chloride, ethylene oxide, ethylene glycol, acrylic acid, ethyl acrylate, and propylene oxide. And these are the approximate capacity. Next. Okay, so our plant will be done in the Kerteh, Terengganu. We have chosen that as our site selection due to several reasons, such as they have neighboring enterprises that can provide raw ingredients, and there are a range of policies and incentive programs implemented in the Terengganu state government, and also it is also a petrochemical hub now, transformed into a petrochemical hub, and it houses the Petronas Petrochemical Integrated Complex that links the entire range of the oil and gas value chain. Okay, next.
Next, I will present the improvement. Actually, for last sem, our weightage for every team is very messy. So for this semester, we standardize our weightage. As you can see, the circle in the table there. I think that's all for me. So I will pass to the next person. Next slide. Okay, this is the team there who handle the centralized system. For team 31, they will handle heating utility for flue gas. 32 will be steam. 33 will be cooling utility, chill water. 34 will be wastewater system. 35 will be waste gas system, and 36 will be cooling utility, cooling water. And next.
Okay, so for the steam heating utility, so based on the design team in our pool, the utility required is low pressure steam and high pressure steam. So medium pressure steam is not required based on the after heat integration. So to accommodate the flow rate of the amount of steam required, we will be using 5 boilers to accommodate the steam, and the steam produced per boiler will be around 121,000 kilogram per hour. And the fuel required for each boiler is around 5,222 kilogram per hour. Next slide. Okay, so this is it shows a few equipments from the steam utility. So we'll be using 5 boilers as mentioned before, and also 5 turbines and 5 deaerator. So these are the costs. So the high pressure steam will be sent to the teams that need loading of the wind turbine, and then the both saturated liquid after you being used up will be mixed and sent to a condenser and will be sent to the boiler again. Okay, next.
We move on to the flue gas hot utility. We collected all the flue gas required by all the design team, and the total flue gas needed is 981,205.16 kilogram per hour. Then the heat required is 2,071,469.77 kilowatt. Later we calculate the fuel required and the air required by using the stoichiometric chemical equation and the heat capacity equation. Next. This is the PFD diagram of the flue gas hot utility. The equipment include the furnace, heat exchanger, electrostatic precipitator, and the denitrification unit. The use of the electrostatic precipitator and the denitrification unit are to remove the fine particles such as the smoke, dust, and the nitrogen dioxide in the flue gas before discharge to the air. Next. This is the profitability analysis. The first table is the calculation of the total bare module cost, and the bottom is the total gross capital cost. The total gross capital cost is around 425 million ringgit. Next.
Okay, and next, this is for the total capital investment. So after going through the direct costs and indirect costs, which includes the instrumentation, piping, engineering supervision, construction expenses, and so on. So the total capital investment that we have calculated is around 1.6 billion ringgit Malaysia. Next. And this table shows the operating costs. So for each unit, we will assign one operator per unit. So the total annual operating labor cost would come up to 2.6 million ringgit. And then the utilities used, we'll be using, as mentioned before, low pressure steam, high pressure steam, and flue gas. So which comes up to 275 million ringgit per year. And also the power consumption for utilities such as pump, turbine, and electrostatic precipitator. So the total annual hot utilities operating costs, which includes the labor costs and also the utility costs, would be around 285,000 million ringgit per year. Next.
Next, I will continue with the centralized coal utility system. This table shows the cooling and chill water requirement for pool 7. The total cooling water needed is about 1.1 million kg per hour, while for the chill water needed is about 216,000 kg per hour. Next slide. Okay. This figure shows the process flow diagram for centralized coal utility system for pool 7, which consists of chill water system and cooling tower. As shown in this figure, there are 4 types of stream, namely cooling water, which represent in blue line, chill water, which represent in green line, refrigerant R717, which represent in purple line at the refrigeration cycle, and ambient dry air, which represent in black line. In this process, induced counterflow mechanical draft wet cooling tower is used instead of natural draft cooling, as it is more effective than natural draft. Counterflow tower potentially can save energy in the long term. While for the refrigerant, ammonia R717 is used instead of tetrafluoroethane R134A because ammonia is more environmental friendly as it has zero global warming potential. Next slide.
So the table on the left shows the equipment costing with the total bare module cost of 142.8 million ringgit and the total capital investment of around 1 billion ringgit. So for the labor cost, one operator is employed per unit operation per shift. So the total annual operating labor cost is around 23.1 million ringgit, which gives the total annual coal utilities operating cost is about 132.6 million ringgit.
Okay, now turns me to present about the waste gas centralized system. So in order to treat the waste gas from the pool 7, so we have to compare all the techniques and choose the best one. So it is including the incinerator, flare gas without and with recovery system. So based on the comparison, we choose the flare gas with recovery system because it can treat a larger flow rate of the waste gas. It is suitable for any concentration, it's visible flame, and it also can reduce the greenhouse gas emission due to the less flaring occur, has less noise and has a lower operating and maintenance cost. Next slide. Okay, this is our PFD of the flare gas recovery system. So based on this PFD, it can produce the flue gas and transfer it to the hot utility centralized system. It also can recover and reuse the hydrocarbons such as the ethylene oxide, which is separately to reduce the waste of the materials. It also can reduce the carbon dioxide emission and lead to less production of greenhouse effect and global warming. It also reduce the noise and heat radiation, reduce the air pollution problems, and lastly is it can extend the life of the flame stick. Next slide, please. Okay, this is our composition of the gas waste from the pool 7. Next slide.
Next is the equipment costing and the total capital investment. So there is four main equipment, which is the flare itself, knockout drum, liquid ring compressor, and three-phase separator. So for the total bare module cost, which is around 2.2 million. And from this, we can get grassroots capital, which around 4 million. And also we can get the total capital investment, which is around 8.8 million. Next.
Thank you, Prima. So, Assalamualaikum and good evening. My name is Haikal and I will present Pool 7 Wastewater Treatment Plant. In general, the Environmental Quality Act EQA 1974 specifies two standards for effluent discharge, which are Standard A is applicable to discharge into any water within any catchment areas, and Standard B is applicable to discharge into any other inland water or Malaysian water according to the Malaysian standard for effluent sewage discharge. So, Pool 7 will focus on treatment that complies Standard B. Next slide, Shaira. Okay, this is the details for each component wastewater in the Pool 7. All the value are come from simulation assist from each team. Next slide. According to the United States Environmental Protection 2011, the wastewater treatment facility is intended to operate at temperatures ranging from room temperature to 40 degrees Celsius and pressure less than 4 atm. The wastewater treatment started with the waste stream from team 36 entering the neutralization tank, which is a unit operation that serves its function as a neutralization for the sodium hydroxide. Next, the wastewater effluent from the neutralization tank will enter a mixer with wastewater stream from other teams. Then continue with aeration of wastewater, which is a process of adding air or increased oxygen to a specific level to allow aerobic biodegradation of the pollutant in the wastewater. After that, it enters the clarifier, which the main goal is to separate water and sludge from the treated wastewater. Next, the waste activated sludge will go through a stabilization process in anaerobic digester. The sludge coming out from an anaerobic digester, then undergoes a dewatering process by using a rotary vacuum filter before final disposal. The top treated water from the clarifier will go through a disinfection process to ensure that the bacterial concentration in treated wastewater is not higher than specified bacteria concentration before release to the environment. To ensure the chlorine level released to the environment at acceptable level, activated carbon adsorption is used. Lastly, the effluent from activated carbon adsorption tank will be nearly pure water and is safe to be recycled back to the plant in Pool 7, and some of them will release to the environment. Next slide. So for the purchase equipment cost for wastewater wastewater system, total bare module cost is around 8 uh, 8 billion ringgit, and for the grassroots capital is estimated around 16 billion, and for the total capital investment TCI is around 107 billion ringgit measure. Next, that's all from me. Thank you.
Oh, I'm sorry. Assalamualaikum and very good afternoon. My name is Ashraf Arifin from Team Design 32. As you can see on your screen is the layout for pool 7. As you can see on the screen, the plan has two entrances, which the first one is the main entrance at the front and another one is at the back, followed by two outdoor car parks and two guard houses. Inside the gate, the plant is further divided into two main areas, mainly the producing area and the safe area. The producing area includes pool 7 team design plants and also integrated utility system. The utility system consists of flue gas system, boiler system, evaporator, cooling tower, flare, and wastewater system. Safe area, on the other hand, consists of main energy supply, canteen, main control room, workers hall, office, laboratory, domestic waste handling area, warehouse, and firehouse. This layout is planned to keep the size of casualty minimized in case of emergency. Okay, next.
Assalamualaikum and hi, my name is Nur Ain, representative from Group 31. I'm going to explain about Pool 7 emergency site layout. Emergency site layout consists of plan layout and emergency evacuation route, where you can see in the slide with the red arrow, which was developed in order to keep personnel and visitors safe and quickly leave the premise that should sign of emergency situation. The emergency plan layout also can make sure the workers safe from fatality or injuries or exposure of dangerous chemicals. The emergency plan was developed with the knowledge that all buildings are not fireproof and fragile, which is why all workers should be in emergency assembly area whenever emergency situation arises. That's all from me. Now I'll pass to the next presenter.
Thank you, Ain. So now we are going to look at the overall cost analysis and look at the comparison between non-integrated plant without centralized system and integrated plant with centralized system. So first is savings in raw material. In integrated plant, the raw material cost is cheaper because some plant, their product is a raw material for another plant. For example, plant 33 will produce acrylic acid and plant 31 will use the acrylic acid produced as a raw material to produce a higher value product, which is ethyl alkali. And same goes with plant 30T, where they obtain their raw material ethylene oxide for plant 35. So because of that, we can save up to 45% in raw material. Next is savings in terms of labor costs. So non-integrated plant, they need more manpower to operate their own utilities, while integrated plant, they require less manpower since the utilities and waste system are centralized. So in the end, we can reduce the labor cost and save up to 51%. Finally, for logistics, for integrated plant, the chemicals are transported by the tanker, while integrated plant, the chemicals are transported in the pipelines. Since the transportation by pipelines is much cheaper, we can save up to 91.82% in logistics. Next, please.
Okay, thank you, Arfa. Hi, it's me again, Mama Aika. So we move to manufacturing and production costs. As we can see in the table, Verbal integrated plant has a higher total capital investment compared to non-integrated plant due to the capital cost in building centralized system and utilities. But the operating cost of the plant reduced after Verbal integration, and it leads to the integrated plant has a higher net annual profit than non-integrated. Our Pool 7 also achieved increment in after-tax of return estimated around 148% after applying Verbal concept. Next slide, Shaira. According to Investopedia, cash flow is the amount of cash that comes in and goes out of a company over the course of a certain amount of time. As we can see the comparison, Pool 7 have achieved payback period estimated around 1.8 operating years after 3 years of startup period. This means the integrated plant will start earning profit after the payback period, which is around 4.3 years in total, while payback period for non-integrated estimated around 13 years after 3 years of startup period, which is too longer time than integrated plan. Percentage of IRR also have huge difference between non-integrated and integrated plant, which are 3% and 86% respectively. Next slide.
That will be overall environmental benefit analysis. Okay, before the bourbon, usually we will use the heater or the cooler for to heat our stream. After we use the bourbon, we produce the heating utility and the cooling utility. So we will less use the electricity. We will be reduce the electricity usage around 70.72%. Besides, because we need to use fuel to produce the steam from the boiler, so we may use 5,000 something of the methane gas per hour. Okay, so all of this will reduce around 70.65% of carbon dioxide emission. So next slide. So for wastewater emission, due to we have the wastewater system, so we can reduce 81% of the wastewater. And same goes to the waste gas emission. We will reduce like 90% since we have the waste gas system. So next slide.
Okay, for the sustainability analysis, for the hot utilities, we use steam as one of our heating medium, which is known to be non-toxic and also heat erasable. So the application of steam as the clean energy is actually consistent with United Nations goals of ensuring the universal access to affordable, dependable, sustainable, and also modern energy under SDG number 7. Besides that, in the flue gas centralized system, we also apply the electrostatic precipitator and also denitrification unit to reduce harmful particle in the flue gas system. So the application of this equipment is actually directly related to SDG number 12, which is to ensure the sustainable consumption and also production practices. On the other hand, for the cold utility, we utilize ammonia R717 as our refrigerant. So it is known to be to has low net environmental impact, and it can be linked with the SDG number 3 and also 13, which mentions that it is critical to employ chemicals, substances that has low environmental impact and to neutralize hazardous chemicals before release it to the environment. Besides that, we also provide a continuous water cycle in the cooling and also chilling water system in order to reduce water and energy consumption. And this practice has been widely accepted in the industry, as what the UN has advocated in the SDG number 12. For the wastewater treatment, we applied activated sludge process system, which is known to have low installation costs and able to provide high quality flow of water, which is due to the activated carbon that is implemented in the treatment process, and this can guarantee the chlorine level in the treated water is at acceptable limit before release it to the environment. And these practices has been highlighted in the SDG number 6. On the other hand, for the waste gas treatment, so in this centralized system, the ultimate purpose of it is to treat waste gas from the that is produced by the sub production plants, and in order to reduce the CO2 emission or other greenhouse gas emissions. And this is directly related to SDG number 13, which is related to the climate change. So that's all from us. Thank you.
Okay, thank you, Seven, for the presentation. So I would like to invite the first panel, Dr. Zaki.
Hello team. Pool number 7. Thanks for the presentation. So slide number 13, 5 boilers, 175 million ringgit. So what kind of boiler is that?
We will be using the water tube boilers.
So what kind of power? How many how many thousand pound per hour? Because I think it's too expensive.
Because in order to accommodate our the amount of steam required for each design team, we are required to use 5 boilers.
5 boilers at one go?
Yes.
So the 5 boilers have equal pounds per hour capacity.
Yes.
Or how do you measure the power? Is it by watt, kilowatt, joule, or what?
Kilowatt.
How many kilowatt? I didn't recall.
Can you previous slide, please? Page 12, slide number 12. Yes, so the heat required per boiler is around 55,000 kilowatt.
And then I can see that you are also occupying, not to say occupying, you are also using high pressure steam. So the boiler is including high pressure boiler, is it?
Yes, high pressure boiler.
Okay, so how many high pressure boiler, or how many high pressure boilers, and how many utility boiler for low pressure steam?
Actually, we are using 5 high pressure boiler, and then we'll be using the turbine to reduce the pressure.
Okay, I doubt that. Maybe other industry panel can comment on that. That is, for me, unacceptable. So it's better if you want to use low pressure boiler, low pressure steam, you need to have a normal utility boiler. And then for high pressure boiler, then you use for high pressure steam. Okay, so you need to know how much, you already have here your demand requirement. This is flow rate, okay? This is not the joule or power or kilowatt or something like that. So you need to have the actual requirement, and then only you can calculate to get how many, what kind of utility boiler, the small boiler to get low pressure steam, and also how high pressure boiler. Okay, that's one thing. Okay. And obviously high pressure boiler such as GEKA, GEKA, that's a brand of the high pressure boiler, it will be very expensive. Okay, but for utility boiler, normal boiler, you can get it quite cheap. Okay, I mean cheaper, far cheaper than high pressure boiler. Okay, thank you, Mr. What's your name? Surya. Okay.
Surya.
Okay, then I don't know what slide number because it's not shown just now, but the heating utility part. Heating utility. Is it this one or the other one?
Is it flue gas or steam, Doctor?
Aduh, tak ingat. Dia tak ada nombor. Dia tak ada page number tadi. Because I before this. Okay, let's cancel it. Okay, let's go to cooling utility. The one that you have CT 100.
Okay.
So next time need to ensure you have a clear slide number shown. Some of the slide have slide numbers, some don't have. Oh, okay, this one. Okay, who's responsible for this?
My team, Doctor.
Siapa? Syahira, awak?
Yeah.
Okay, Syahira, you have a very gorgeous CT 100 symbol there. I mean, picture, icon or picture, I don't know. But that is not a cooling tower for refinery. So that is for what? This is a cooling tower for nuclear power plant. Okay, so this is not the actual symbol. Okay, so you need to improve lah, correct this. Okay.
Sure, Doctor. Thank you, Doctor.
And then go to the wastewater treatment site. Okay, this is out of context or topic, but I just want to ask you whether when you want to design any wastewater treatment plant, do you include in your cost, or do you think that you need to have an endorsement from DOSH, Department of Safety and Health, or and DOE in order for you to build a wastewater treatment plant in terms of design? Anybody can answer that?
From my opinion, I think yes, Doctor.
From your opinion, okay.
Because of we need to follow the regulation, the outcome, and the outcome is come from the Malaysian government.
Okay.
We need to have a procedure.
Okay, good attempt for answering that. Okay. By the way, just to let you know, okay, everybody here is chemical engineers, right? So, if the regulation has stipulated that if you want to build a wastewater treatment plant, it need to be you need to obtain the design endorsement from DOE. DOE, and then a professional engineer having chemical engineering degree, okay, should endorse, should sign, okay. So this is just to let you know, so that you are aware that if you are a professional engineer having IR, okay, your IR has value. Okay, so it's not that only electrical engineer, mechanical engineer, and also civil engineer only. Okay, chemical engineer will have their say in terms of confirming, checking, and verifying the design for wastewater treatment plant. And before that, it also need to go. I mean, the entire facility asset require you to go through the EIA process, environmental impact assessment process, and the DOE as well. Okay, so that's just advertisement lah. Not to say, I mean, this is side information. Okay, please go to
Doctor,
your.
thank you.
Welcome. Slide number 35. Okay, slide number 35 is showing plan layout, which I think is Syaira, siapa yang lukis ni?
Me.
Me?
Yes.
Who?
Ashraf.
Ashraf. It's not really attractive. Okay, it's kind of boring, but I must say I give credit to you because you draw the storage tank bulat-bulat, circle. So that finally I see a plan layout that have a logical shape lah for storage tank. So just now, if I see a plan layout from group number 1 and group number 4, they don't even have product storage tank. Okay, this is just to recap that. Okay, group number 1 and group number 4 don't have any product or feed storage tank. Group number 2, sorry, pool number 2, pool number 3, pool number 5 and 6, you have put the site location lah for the storage tank lah. But this one looks nice. So well done lah. Baru nampak macam plan lah kan. Okay, then please go to waste gas treatment. I think this Shahira mentioned just now. The one the waste gas treatment showing low CO2 emission. You presented this one last, the final one.
Is it this one, Doctor?
Not this one. You have a table there, and then the last point is waste gas treatment. This one. So you have related this to SDG, and then waste gas treatment associated to low CO2 emission. So of course you want to reduce it there, but then what about the other part of the plant?
Sorry, can you elaborate the question? I couldn't.
Okay. For waste gas treatment, low CO2 emission. Maybe you have done something, and then the emission of CO2 have been lowered. But what about other places in the plant? What about the usage of the massive usage of other utilities, the pump, chiller, and so on?
Oh, so it's actually not just in the waste gas treatment centralized system, it's actually also in the hot utilities as we are releasing flue gas, right? So but in the main purpose in the waste gas treatment is actually to reduce the CO2 emission. So that's why I mentioned that table.
Okay. Okay, thank you very much. Pool number 7. That's all from me.
Thank you, Doctor.
Bye.
Thank you, Dr. Zaki.
Welcome.
Now I would like to call industrial panel. Maybe we'll start with Mr. Fidaus.
So hi everyone. Okay, just quick one from me. Add up from IR Zaki on the plan layout. Okay, you can go to that. Okay, everything is good. Again, just where is your loading and unloadings for storage tank? So meaning like you any storage tank, from this storage tank you have to distribute to your customers and all that. Did you consider the loading bay or unloading bay for logistic part?
Alright, to answer to that question, I did consider the loading area, but I include the loading area into the storage area here in mind. And so the space in front of the storage area is also can be a place for truck to park, and also can be
All right,
emergency.
okay, that nice, but maybe you can show on this planet out. For my suggestion. Okay, so we go to the next one on the steam generation flow diagram. But it's more onto general because it's all team to something similar. But that's just to test you, I think. Okay, you see from generator, and then is it the boiler feed water from generator? You combine with air, then you feed to the boiler. Do you
Yes.
Okay, maybe you have to correct that lah. The boilers is not the boiler feed water will feed with air. Then where should be the steam production, right? Because air and the fuel required for the combustion, it will be goes to the off gas line. So it should be a separated system. Then the air, then the water will be in because this is tube, and then it goes to the tube side, and then goes to the steam production. Let's just comment on the diagram. So it's very confusing. And then just to test you another one, how you transfer from the makeup water tank to the generator. You have pump or the
Yes,
gravity flow
we'll be using pump.
using pump, right? So
Yes.
okay, for example, you have the pump. The pump will be before the heat exchanger or after the heat exchanger.
It will be after.
Why? Why after?
Because we reduce the temperature first, and then we would pump it to the aerator.
Are you sure? What exchanger? Why do you need the heat exchanger for the generator? From the makeup water?
To preheat.
Increase preheat, right? So you preheat mean that from your justification that you want to cooling down, right? But just quick one is normally the pump will be before the heat exchanger, because you design the heat exchanger, you need to know the minimum velocity from the pump basically. That's all. All right. Okay, I think that's all for me.
Thank you.
Thank you.
Thank you, Mr. Firdaus. So I would like to call the last panel. Maybe I will call Mr. Ezra.
I have no comment. I will comment in the report as it's already 6 p.m.
Okay, maybe I will call Miss Nur Falisa.
Very quick question. Can you go to the cooling water system? Okay. If you look at your cooling water supply and cooling water, the cooling water supply pump P101, you have one pump only, right? Okay, and then your flow rate is very big there. So your pump is very big. So can you go and revisit the pump selection I think you can find the typical information for water pump. What is the biggest capacity, and from there you can decide on your number of pump. And also for rotating equipment, normally we will have spare because the equipment need to undergo the preventive maintenance program. So you need to have a spare for rotating equipment. So maybe you can revisit also this. And
Just to add, actually for the pump 101, we have two actually. But in terms of the standby kind of pump, we didn't consider it before, but we will include it in the next.
If you have two pun still very big. So kat situ
No.
berapa kg power tu? How much is it? 1
million.
1 million kg power is about 1 million meter cube per hour, right? So do you have pump that size?
Understood.
Okay. This one you can Google actually the typical water pump, and then you can check. The information is available in the internet. Thank you. That's all.
Okay, Miss. Thank you, Miss.
Okay, thank you, all sevens. I think we already reached to the end of this session. So first of all, I would like to apologize because it's already 6:10 p.m. because each panel excited to share the feedback as well as the comments to you guys. So as a conclusion for today's session, I would like to thank to all panels, in the industrial panels, Mr. Ezral, Ms. Nur Falisa, Mr. Muhammad Fidaus, UTM panel, Prof. Sharifah, Dr. Zaki, and Dr. Lim. Thank you for the comments given by our panels. These comments are very valuable and useful to our students in order to improve their knowledge as well as the plant design project. And for students, thank you for your great presentation. I'm not sure when you have to submit the revised version. Maybe you can ask your coordinator later. And before we dismiss, maybe we can have a photo session. I hope that everyone turn on the camera. Okay. Okay, it will take a while because we have few pages here. So I will start with the first page now. Okay, smile. 1, 2, 3. Next page. One, two, three. Third page. 1, 2, 3. Okay, okay, only 3 page turn on the camera. I think that's all for today. Thank you everyone and good luck for your next presentation on the 14th.
Thank you.
Thank you, Doctor.
Thank you, Doctor.
Thank you, everyone. All the best.
Thank you.
Congrats,
Thank you to all
everyone.
panelists.
Thank you.
Thank you, Mr. Ilham.
Keep survive, guys.
Yeah, Doctor.